Among the countless stars that blanket our night sky, it is truly astonishing to think that a vast majority of the universe, about 90%, remains an impenetrable mystery, hidden far beyond our comprehension. The cosmos, stretching out in all directions, is filled with peculiar celestial bodies and phenomena that challenge the very laws of physics, pushing the boundaries of our understanding of reality. From galaxies that twist and turn in strange and inexplicable patterns to planets that harbor secrets about the potential for life beyond Earth, the universe stands as a treasure trove of wonders, waiting for us to unlock its secrets. Dark matter, one of the universe's most tantalizing enigmas, has puzzled scientists for decades. This invisible substance cannot be detected by traditional means, yet it exerts an undeniable influence on the universe. Its presence inferred only through the gravitational effects it has on visible matter. What's astonishing is that dark matter constitutes roughly 26% of the total mass energy content of the universe. Yet, despite years of study, its precise nature remains an enigma. This curious substance has eluded detection, and scientists have proposed various candidates to explain it, from weakly interacting massive particles, WIMPs, to axions, hypothetical particles that are as elusive as they are mysterious. However, none of these particles have been conclusively detected, leaving the question of dark matter's true identity still open. Equally perplexing is the distribution of dark matter throughout the cosmos. Observations of galaxies and galaxy clusters show that they are surrounded by enormous halos of dark matter, but the precise organization and behavior of this unseen matter remain unclear. For example, certain galaxies appear to have far less dark matter than would be expected. Why do some galaxies seem to defy the general pattern? This discrepancy raises important questions about how galaxies form and evolve, challenging our existing cosmological models. Could it be that dark matter behaves in ways we have yet to fully comprehend? How does it interact with regular, visible matter? And how does its mysterious presence affect the growth of galaxies and other cosmic structures? The study of dark matter also raises questions about its behavior on a larger cosmic scale. Structures in the universe, such as vast cosmic webs of interconnected galaxies, suggest a complex relationship between dark matter and gravity. Yet, when scientists simulate the evolution of the universe on a grand scale, they find it challenging to replicate the vast interconnected structures we see today. Are there forces, perhaps even additional dimensions, at play that we have yet to identify? This line of inquiry pushes the limits of our understanding and suggests that the universe may be far more intricate than we can imagine. One of the most intriguing aspects of dark matter remains the question of whether it interacts with itself. If dark matter particles have the ability to collide and interact in ways similar to normal matter, it could help explain strange cosmic phenomena, such as the bullet cluster. In this event, two galaxy clusters collided, creating a unique observational opportunity to study how dark matter behaves under extreme conditions. Could these interactions offer crucial clues about the nature of dark matter and its role in the evolution of the universe? If dark matter does interact with itself in some way, understanding these dynamics could be key to unlocking the secrets of this elusive substance. As scientists dive deeper into these mysteries, each new discovery brings us one step closer to unraveling the unseen fabric that makes up our cosmos. The concept of wormholes, fascinating yet entirely theoretical, emerges from the framework of Einstein's general theory of relativity. Wormholes, in essence, are imagined as shortcuts through space-time, offering potential pathways between distant points in the universe. These hypothetical tunnels could allow for travel between two far-flung locations in a fraction of the time it would take through normal space. The mathematics behind wormholes suggest that such structures, if they exist, would be formed by extreme gravitational forces that curve space-time in profound and intricate ways. But what is most tantalizing about wormholes is their potential to allow not only for travel across vast distances, but in some interpretations, even for time travel. Imagine stepping into a tunnel in your backyard and emerging millions of light years away in the blink of an eye, or even stepping into the past or future. However, the scientific community remains cautious about the reality of wormholes. While their theoretical foundations are rooted in the established laws of physics, no evidence of their existence has been found. Furthermore, many physicists speculate that if wormholes do exist, they could be highly unstable. They might collapse before anything could traverse them, or require the presence of exotic matter, strange material with properties that allow them to remain open. This exotic matter has never been observed, leaving the possibility of wormholes open yet uncertain. Could the mysteries of dark matter, strange galaxies, and the very fabric of space-time hold the key to unlocking these cosmic passages? For now, wormholes remain one of the most fascinating and enigmatic possibilities in the universe, lying just beyond the reach of our current understanding. As humanity continues to explore these cosmic puzzles, every new discovery brings us closer to answering some of the most fundamental questions about the universe. What lies hidden in the dark corners of space? How does dark matter shape the universe, and what secrets does it hold? Could wormholes provide the key to exploring distant realms, or even unlocking the mysteries of time itself? With each breakthrough, we move closer to understanding the vast, unexplored expanse of our cosmos. Yet with each answer we uncover, more questions arise, urging us to continue our quest for knowledge, to look deeper into the night sky, and to embrace the infinite possibilities that await. The exploration of wormholes invites us into the realm of the unknown, challenging the very framework of our understanding about the universe. Wormholes, theoretical passages through space-time, could potentially offer shortcuts to distant regions of the cosmos. If we could harness them, the implications would be staggering. They would reshape our very notion of distance and time, forcing us to reconsider everything we know about travel and the nature of the universe itself. At the heart of the wormhole concept lies the idea of connectedness. Could there be parallel universes, alternate timelines, or hidden dimensions existing side by side with our own? If wormholes were real, they could serve as bridges between these disparate realms, suggesting a vast and intricate web that ties together all of reality in ways far beyond our current comprehension. This opens up the tantalizing possibility that everything we observe is not isolated, but rather part of a larger, interconnected cosmic system. Imagine, if you will, a universe not as a collection of isolated stars and planets, but as an expansive, dynamic tapestry where everything, past, present, and future, is interwoven. The discovery of wormholes would not only redefine our place in the universe, it would prompt us to rethink the fundamental fabric of reality itself. Though wormholes remain speculative, confined to the pages of theoretical physics, they ignite our imagination. As we continue to probe the depths of cosmology and quantum mechanics, the notion of these anomalies stirs our sense of wonder. Could they hold the key to unlocking the future of space exploration? As humanity pushes the boundaries of what's possible, the quest to understand and perhaps even utilize these cosmic shortcuts could usher in a new era of discovery, one that challenges our assumptions about time, space, and existence. Meanwhile, another mystery continues to perplex and excite astronomers: dark energy. Identified in the late 20th century, dark energy has become one of the most intriguing and enigmatic forces in the universe. Initially detected when scientists observed that the expansion of the cosmos was not only continuing but accelerating, this unexpected discovery ignited a quest to find an unseen force capable of explaining such acceleration. That force was dubbed dark energy. Picture the universe as a vast balloon, gradually inflating. As it expands, the galaxies on its surface move further apart. In the early stages, gravity, the force pulling everything inward, was stronger than any outward force. However, something changed. Dark energy seems to have altered the balance, making the outward push of the universe's expansion stronger than the inward pull of gravity. This change has set the universe on a course toward infinite expansion, where galaxies drift farther apart, eventually leaving the universe colder, emptier, and more isolated. Dark energy is thought to make up approximately 70% of the universe, yet it remains elusive. It does not interact with matter in the ways that we might expect. It doesn't emit light or radiation, which makes it nearly impossible to detect directly. Instead, scientists infer its presence through its effects on the cosmos. Its influence is visible in the way galaxies and other cosmic structures are being stretched apart over time. The role of dark energy is central to ongoing debates about the fate of the universe. Will it continue expanding indefinitely, Or will a deeper understanding of this force reveal new revelations about the universe's ultimate destiny? With each new piece of data, scientists inch closer to answering these profound questions. As we explore the nature of dark energy, we not only learn about the universe's past, but also come closer to unlocking the mysteries of its future. Equally baffling are fast radio bursts, FRBs, a cosmic phenomenon that has left scientists scratching their heads since their discovery in 2007. These are incredibly brief, yet extremely powerful bursts of radio energy, lasting only a few milliseconds. What makes FRBs particularly intriguing is their origins. They seem to come from vast distances across the universe, and yet despite their brief nature, some of these bursts release as much energy in a single millisecond as our sun does over an entire year. Such a concentration of energy challenges our understanding of the forces at play in deep space. Several theories have been proposed to explain the origin of FRBs. One leading hypothesis suggests that magnetars, neutron stars with incredibly strong magnetic fields, could be responsible. When a magnetar experiences a dramatic shift in its magnetic field, it may release enormous amounts of energy, potentially in the form of radio waves, which could explain the bursts we observe. This theory gained traction when scientists detected repeating FRBs that appeared consistent with the behavior of magnetars. Other possibilities point to the aftermath of cosmic cataclysms, such as the collision of neutron stars or black holes. These explosive events could unleash enormous amounts of energy in the form of radio waves and other detectable signals, creating what we observe as fast radio bursts. Despite decades of research and numerous theories, the true origin of these enigmatic signals remains elusive. As technology improves and more observatories come online, we may one day uncover the true source of FRBs, whether they be a product of stellar evolution or the result of more exotic cosmic events. Alongside these cosmic mysteries, gravitational waves offer another exciting frontier of exploration. These ripples in the very fabric of space-time, created by some of the most violent and energetic events in the universe, such as the collision of black holes or the explosion of stars, were first predicted over a century ago by Albert Einstein's general theory of relativity. Yet it wasn't until 2015 that gravitational waves were detected directly by the Laser Interferometer Gravitational Wave Observatory, LIGO, marking a groundbreaking achievement in astrophysics. LIGO uses a highly sensitive technique called laser interferometry to detect these waves. By measuring the interference patterns of laser beams traveling along two long arms positioned at right angles, scientists can detect the tiny distortions caused by a passing gravitational wave. These distortions are incredibly small, on the order of a fraction of the width of a proton, but they provide a direct observation of space-time being stretched and compressed. Since that first detection, gravitational waves have opened a new window into the universe, allowing scientists to observe events that were previously invisible to conventional telescopes. One of the most exciting developments has been the ability to observe the mergers of neutron stars. This provided not only gravitational wave data, but also electromagnetic signals, enabling astronomers to study these events from multiple perspectives. The observation of such events has revealed new insights into the production of heavy elements like gold and platinum, elements that are crucial to understanding the origins of some of the universe's most fundamental building blocks. The study of gravitational waves continues to be one of the most promising areas of modern astrophysics, offering unparalleled insights into the most extreme and energetic processes in the universe. With each new detection, we move closer to unlocking the secrets of space-time itself and gaining a deeper understanding of the forces that shape the cosmos. The discovery of these waves has not only confirmed Einstein's predictions, but also opened up a new era of exploration, one that promises to reveal even more about the mysteries of the universe. The future of astrophysics is filled with excitement and possibility. As we continue to explore the vast expanse of space, technologies like LIGO and the ongoing investigation into wormholes, dark energy, fast radio bursts, and gravitational waves promise to challenge our understanding and drive us to new frontiers. Each new discovery opens up even more questions, and with every answer we gain, we come one step closer to unraveling the true nature of the universe. Moreover, the discovery of gravitational waves has led to a monumental shift in our understanding of the cosmos. Thousands of gravitational wave events have now been cataloged since that groundbreaking first detection, each one offering a treasure trove of invaluable insights into the workings of the universe. From the mysterious behavior of black holes to the hidden dynamics of neutron stars, gravitational waves have proven to be the key to unlocking the deepest questions surrounding gravity and the fundamental forces that govern the fabric of space and time. As technology continues to advance, the horizon for new and exciting discoveries grows ever larger. Gravitational wave astronomy holds immense potential, not just for answering existing questions, but for challenging and refining our most established theories. These waves push the boundaries of our knowledge, revealing new phenomena and testing the limits of our understanding. Each detection is a reminder of how much we still have to learn and how much more the universe has yet to reveal about its most enigmatic and powerful components. The journey of unraveling these cosmic mysteries is far from over. In fact, it's only just beginning, inviting all of humanity to contemplate the profound and untapped depths of our universe. One of the most captivating glimpses into the early universe comes from the cosmic microwave background radiation, or CMB. This ancient light is the afterglow of the Big Bang, a remnant of an era when the universe was dense, hot, and filled with radiation. As the universe expanded and cooled, this light was released roughly 380,000 years after the Big Bang, marking the moment when neutral hydrogen atoms could finally form. Now the CMB fills the entire universe, a faint but pervasive glow permeating every corner of space. However, this radiation is far from uniform. It is laced with anomalies, tiny temperature fluctuations that offer profound clues about the universe's origins and its early evolution. These temperature variations, known as anisotropies, represent small differences in temperature across the sky. They arose from the density variations present in the early universe, which eventually led to the formation of galaxies and the vast structures we observe today. The patterns of these anisotropies point to an event of tremendous significance, the inflationary period of the universe. This rapid expansion, believed to have occurred in the first fractions of a second after the Big Bang, would have smoothed out the universe and set the stage for the formation of all cosmic structures. The seeds of galaxies, stars, and even clusters of galaxies were planted during this phase, and understanding these patterns helps scientists trace the evolution of the universe from an infinitesimally small point to the sprawling cosmos we know today. Among the anomalies within the CMB, one of the most intriguing is the so-called cold spot, a region where the temperature is unusually lower than its surroundings. Some scientists have speculated that this cold spot may indicate the presence of a massive supervoid, an enormous empty region in space that could suggest the universe is behaving in ways we did not anticipate. Even more speculative are ideas linking this cold spot to the possibility of interactions with another universe, a hypothesis inspired by the theory of the multiverse. Although controversial and unproven, these ideas spark heated debates among cosmologists and prompt them to reconsider the very nature of our universe. Could our universe be just one among many? The cold spot remains one of the many mysteries that fuel curiosity and push the boundaries of theoretical physics. Additionally, large-scale patterns, such as the alignment of anisotropies, continue to baffle scientists. These alignments seem to challenge the standard model of cosmology, leading to new ideas about the topology and overall structure of the universe. Are these alignments a sign of a deeper order, or are they simply the result of chance? As cosmologists continue to unravel these complexities, each new discovery becomes a stepping stone toward refining our understanding of the universe's early moments and how it grew into the vast and intricate system we observe today. Pulsars, another remarkable phenomenon in astrophysics, add yet another layer of wonder to our understanding of the universe. These highly magnetized, rotating neutron stars act like cosmic lighthouses, emitting regular pulses of electromagnetic radiation as they spin. Just as a lighthouse's beam sweeps across the sea, a pulsar's beam sweeps across space, and if it aligns with Earth, we perceive regular pulses of radiation. These periodic signals are incredibly reliable, making pulsars natural cosmic clocks. Some pulse several times every second. Predictability allows scientists to make incredibly precise measurements and provides a powerful tool for studying the universe. What makes pulsars so captivating is their extreme density. They are so compact that a single neutron star can have a mass greater than that of the Sun, but be confined to a sphere no more than 20 kilometers in diameter. The immense gravitational and magnetic fields present in these stars provide a laboratory for studying matter under conditions unlike any found elsewhere in the universe. By observing the radiation emitted by pulsars, scientists gain valuable insights into the composition of these stars and the nature of space itself. Pulsars also play a crucial role in testing the theory of general relativity. Some pulsars exist in binary systems, where they orbit a companion star. These binary pulsar systems act as natural laboratories for testing predictions about gravity and the fabric of space-time. As the two stars orbit each other, they emit gravitational waves, ripples in space-time that can be detected by observatories. These gravitational waves offer a new way of probing the universe, revealing details about black holes, neutron stars, and the very nature of space-time itself. The study of these waves has opened up entirely new frontiers in astrophysics, providing a deeper understanding of the most extreme environments in the cosmos. In sum, the study of gravitational waves, the cosmic microwave background radiation, and pulsars has revolutionized our understanding of the universe. Each of these phenomena offers a unique and captivating glimpse into the workings of the cosmos, and each new discovery propels us further down the path of uncovering the deepest mysteries of space. The universe is vast, mysterious, and full of wonders, and as our tools and techniques continue to evolve, so too will our understanding of the cosmos and our place within it. The journey of exploration and discovery is just beginning, and the wonders that await are boundless. Pulsars are not just fascinating celestial objects, they are key to unlocking the most profound mysteries of the universe. Their rapidly rotating, highly magnetized nature makes them reliable cosmic beacons. As they emit regular pulses of radiation, pulsars offer a unique window into the vast expanse of space, revealing insights that are crucial for understanding the evolution and structure of the universe. The light emitted by pulsars serves as a cosmic flashlight, illuminating the complexities of the interstellar medium, the matter that fills the space between stars. By studying the pulses, scientists can determine the density, temperature, and even the composition of this medium, offering a deeper understanding of how stars form and evolve. In addition, the behavior of pulsars gives us a glimpse into the dynamic processes that shape galaxies. The distribution of pulsars, their varying luminosities, and the way their pulses interact with surrounding matter provide us with invaluable data about the formation and life cycles of stars, as well as the forces that govern galactic dynamics. As technology advances, we continue to push the boundaries of pulsar research, uncovering more secrets about these cosmic beacons and their role in the broader cosmic tapestry. These studies not only deepen our understanding of the universe, but also guide us toward answers to fundamental questions about the origins of the cosmos itself. A rogue planet is one of the most mysterious and captivating phenomena in astronomy. These planets are not tethered to any star, wandering freely through space, far from the familiar orbit of any celestial body. Rogue planets are thought to be the remnants of once stable planetary systems that were disrupted, possibly by gravitational interactions with other stars or celestial bodies. They may have been ejected from their home systems during chaotic events, leaving them to drift aimlessly through the vast darkness of the universe. Unlike the planets we know, such as those in our solar system, which revolve around a central star, rogue planets are solitary, moving through the emptiness of space without the warmth or light provided by a sun. Estimates suggest that there may be far more rogue planets in our galaxy than there are stars, a realization that presents a fascinating and somewhat unsettling view of the universe. The idea that the cosmos could be teeming with these solitary wanderers hidden in the dark void is awe-inspiring. However, because rogue planets do not emit light of their own, they are incredibly difficult to detect. Instead of shining brightly like stars, they may only radiate weak thermal emissions, which require sophisticated instruments to observe. As technology advances, however, astronomers have started to uncover more examples of these elusive objects. For instance, PSO J317 522, discovered in 2013, is a rogue planet that is about 6 to 10 times the mass of Jupiter. Located approximately 60 light-years from Earth, this young free-floating planet provides valuable insights into the formation of planetary bodies. Another noteworthy example is CFBD J21494-72, 43, which has intrigued astronomers since its discovery in 2012. Both of these planets challenge our traditional understanding of planetary formation and raise profound questions about the processes that govern the birth and life cycles of planets. With advancements in observational technologies, it is likely that we will discover many more rogue planets, revealing a vast and complex universe full of planets that once belonged to stable star systems, but now roam the cosmos, free from the gravitational pull of a sun. These discoveries suggest that planetary systems may be far more diverse and dynamic than we had ever imagined. Magnetars are among the most extraordinary objects in the universe, distinguished from typical neutron stars by their immensely powerful magnetic fields. While neutron stars are already remarkable for their density and compactness, created from the remnants of massive stars that have undergone supernova explosions, magnetars take this to an extreme. Their magnetic fields are far stronger, reaching up to 1 quadrillion times the strength of Earth's magnetic field. This makes magnetars some of the most magnetically intense objects known to science. The origin of their incredible magnetism can be traced back to the collapse of a massive star into a neutron star. As the star implodes, immense gravitational forces compress its material, and if the pre-existing magnetic fields align with this collapse, they are amplified to extraordinary levels. The phenomenon that causes this magnetic boost is known as magnetohydrodynamics, where the movement of conductive plasma within the star generates even stronger magnetic fields. Magnetars are not just more magnetic versions of neutron stars. They are fundamentally different entities. Their magnetic fields influence not only their internal structure, but also the surrounding space environment in profound ways. One of the most astonishing aspects of magnetars is their ability to emit incredibly powerful bursts of gamma rays and X-rays. These bursts occur when the star's crust cracks as a result of changes in its magnetic field, releasing an enormous amount of energy. These emissions can be detected from vast distances, offering a rare opportunity to study the extreme physics that govern these objects. The violent and energetic behavior of magnetars makes them both fascinating and enigmatic, providing researchers with a natural laboratory to investigate the most extreme conditions in the universe. Quasars, on the other hand, represent some of the most luminous and powerful phenomena in the universe. They are formed around supermassive black holes located at the centers of galaxies. As material falls into these black holes, it heats up to millions of degrees, generating enormous amounts of light, especially in ultraviolet and visible wavelengths. This process makes quasars one of the brightest objects in the cosmos, often outshining entire galaxies. One of the most intriguing aspects of quasars is their immense distance from Earth. Many of them are located billions of light years away, meaning that when we observe them, we are looking back in time, witnessing conditions that existed in the early universe. These distant lights provide a snapshot of the cosmos when it was still in its infancy, offering us a unique glimpse into the evolution of galaxies and the universe as a whole. By studying these bright beacons from the past, astronomers are able to trace the history of the cosmos, uncovering the processes that have shaped it over billions of years. Quasars thus serve as essential tools for understanding the evolution of galaxies, stars, and the very fabric of the universe itself. As our understanding of these celestial objects continues to evolve, we are not just learning about isolated phenomena, but also gaining deeper insights into the complex forces that govern the universe. Each new discovery, whether it be a pulsar, a rogue planet, a magnetar, or a quasar, adds another piece to the puzzle of cosmic evolution, guiding us closer to the fundamental truths of the universe. The more we learn, the more we realize that the universe is far more complex and awe-inspiring than we could have ever imagined. Quasars are among the most extraordinary and enigmatic objects in the universe. These cosmic beacons are defined by their incredibly powerful emissions, outshining entire galaxies, and often holding the key to some of the most fundamental mysteries of space. What makes quasars especially remarkable is their tremendous redshift, a phenomenon caused by the expansion of the universe itself. As quasars move away from us at astonishing speeds, the light they emit gets stretched, shifting toward the red end of the spectrum. This shift, referred to as the redshift, provides astronomers with a unique tool to measure the distance to these objects. By analyzing the degree of redshift, scientists can estimate how far away a quasar is, and more importantly, calculate the rate at which the universe is expanding. But quasars do not only serve as markers of cosmic distances. They are dynamic entities with fluctuations in brightness that can vary over time. These variations offer a glimpse into the complex processes happening around the supermassive black holes that reside at the heart of quasars. In fact, quasars are not just some of the brightest objects in the cosmos. They are, in a sense, cosmic laboratories, providing valuable insights into the behavior of matter under extreme gravitational conditions. They offer a look into the very nature of black holes, shedding light on their immense gravitational pull and the behavior of matter as it spirals toward them. The study of quasars has also deepened our understanding of the early universe. The light we observe from these objects today has often traveled billions of years across space, allowing us to peer back in time to an epoch when galaxies were just beginning to form. Quasars, as remnants of this early period, act as beacons that illuminate the past, giving us an invaluable window into the conditions that existed shortly after the Big Bang. Their study not only reveals the power of supermassive black holes, but also provides clues about the development of the universe itself. Despite their brilliance, the mysteries surrounding quasars remain vast. As scientists continue to probe their nature, quasars remain a focal point of astrophysical research, constantly pushing the boundaries of our understanding of the cosmos. Shifting from quasars to another fascinating cosmic entity, brown dwarfs offer yet another challenge to our conventional understanding of stellar and planetary formation. These mysterious objects occupy a unique position in the spectrum of celestial bodies. Often referred to as failed stars, brown dwarfs form in much the same way as stars, but they never accumulate enough mass to trigger the nuclear fusion of hydrogen in their cores. As a result, brown dwarfs are cooler and dimmer than stars, lacking the brilliance that characterizes their more massive counterparts. Brown dwarfs are not quite stars, but they are also far too massive to be classified as planets. Their mass typically ranges between the heaviest gas giants and the lightest of stars, making them an intriguing class of object that defies simple classification. This transitional nature places brown dwarfs in a gray area that forces astronomers to reconsider the very definitions that underpin our understanding of the universe. Celestial bodies are primarily categorized by mass, yet brown dwarfs seem to bridge the gap between the planet and the star, blurring the lines and forcing scientists to rethink the criteria used for such classifications. The existence of brown dwarfs has sparked a significant reevaluation of what constitutes a star. Researchers have begun to question whether temperature, brightness, and mass are sufficient to define a celestial body as a star. In particular, the discovery of brown dwarfs has challenged traditional models of stellar evolution, prompting scientists to reconsider the processes that lead to the formation of stars and planets alike. Studying brown dwarfs could provide crucial insights into the mechanisms that govern the formation of both stars and the planets that orbit them. Moreover, the study of these objects has the potential to unlock deeper mysteries about the early universe and the formation of star systems. Since brown dwarfs never undergo hydrogen fusion, they remain cooler than stars, emitting faint infrared radiation rather than visible light. This allows astronomers to study them in different ways, offering a fresh perspective on the processes that shape the universe. The discovery of these objects has opened up new avenues for exploring the vast and complex landscape of the cosmos, encouraging scientists to question long-held assumptions and explore the full spectrum of celestial phenomena. Ultimately, brown dwarfs represent a crucial evolution in our understanding of the universe. Their existence challenges our traditional models and compels us to explore the intricate relationships between stars, planets, and the processes that govern the cosmos. They underscore the interconnectedness of these celestial realms and expand our understanding of what it means to be a star, suggesting that the universe is far more complex and diverse than we could have imagined. Venus, often referred to as Earth's twin due to its similar size and composition, presents its own set of mysteries, particularly in its dense atmosphere. Wrapped in thick clouds of sulfuric acid, Venus's atmosphere is hostile and uninhabitable by human standards. The clouds swirl around the planet at astonishing speeds, creating an environment where surface conditions are extreme. Temperatures on the surface of Venus can reach up to 900 degrees Fahrenheit, 475 degrees Celsius, hot enough to melt lead. The atmospheric pressure is over 90 times that of Earth's, and the clouds are dense with toxic sulfuric acid, creating an almost impenetrable environment for any potential exploration. Despite these harsh conditions, recent studies have uncovered some peculiarities that have sparked curiosity about the possibility of life existing in Venus's upper atmosphere. In particular, scientists have detected the presence of phosphine in the planet's clouds. Phosphine is a gas that on Earth is primarily associated with biological processes, particularly with the decay of organic matter or the metabolism of certain microbes. The discovery of phosphine on Venus has raised eyebrows because, under the extreme conditions present on the planet, the gas should not exist in measurable quantities without some form of biological activity. This has led to speculation that life could potentially exist in the more temperate regions of Venus's upper atmosphere, where conditions may be less extreme. While the concentrations of phosphine detected are small, they are significant enough to prompt a serious scientific debate about the possibility of life in the clouds of Venus. Could this gas be the product of unknown geological processes, or could it be the result of some form of microbial life that thrives in these high-altitude clouds? The discovery has certainly generated interest among researchers who are now investigating whether the presence of phosphine might be a sign of life, or merely an indication of some unexplained chemical processes at work in Venus's atmosphere. This discovery adds yet another layer to the already complex mystery of Venus, one of our closest planetary neighbors. While the surface of the planet remains inhospitable, the detection of phosphine in its clouds has opened up a new realm of possibilities. Venus's atmosphere, once considered a desolate and lifeless region, may hold more surprises than we could have ever imagined. The debate over the presence of phosphine continues, and as scientists continue to explore the possibility of life on Venus, we are reminded of the vast unknowns that still await us in our exploration of the cosmos. The clouds of Venus, despite the planet's searing surface temperatures, offer a remarkable contrast. The atmospheric conditions found here are far more temperate than the blistering heat of the planet's surface, with the temperature hovering around a comfortable 70 degrees Fahr and the pressure resembling that of Earth's surface. This unique environment gives rise to an intriguing possibility. Could microbial life, adapted to such extreme conditions, thrive in the sulfuric clouds of Venus, far above the scorching heat below? This thought-provoking notion raises fundamental questions about the nature of life itself. It challenges our very definition of life and prompts us to rethink where it might exist. As we continue to explore the peculiar chemistry of Venus's atmosphere, we gain new insights into the resilience of life and its potential to flourish in the most unlikely of places. The search for life beyond Earth is not merely a scientific curiosity, but a quest that expands our understanding of the universe and the boundaries of existence. As missions to Venus advance, scientists are on the verge of discovering whether its clouds might harbor life, or whether this idea is simply a flight of fancy, fueled by imagination. Meanwhile, neutron stars, one of the universe's most extraordinary phenomena, remain a captivating subject of study. These stars are formed from the remnants of massive stars that have exploded in supernovae. When a star runs out of nuclear fuel, it collapses under its own gravity. However, instead of becoming a black hole, it transforms into a neutron star, an incredibly dense object where the matter is packed to unimaginable densities. A mere sugar cube-sized amount of neutron star material weighs as much as a mountain on Earth. This extreme density pushes the limits of our understanding of matter, offering an unparalleled opportunity to explore the fundamental properties of the universe. Inside a neutron star, matter is primarily composed of neutrons, tightly packed in an ultra-dense state that is completely foreign to anything we experience here on Earth. Such conditions enable scientists to study the behavior of matter under pressures and densities far beyond what can be recreated in laboratory settings. The extreme environments of neutron stars allow scientists to probe the forces at play in these extraordinary objects, such as the interactions between subatomic particles, and to refine our understanding of quantum mechanics and relativity. Conventional physics no longer applies at these scales, leading researchers to consider new theories that might unify the fundamental forces of nature. Furthermore, neutron stars are not only valuable for understanding matter, but also serve as cosmic laboratories for studying gravitational waves. When two neutron stars spiral together and collide, they create ripples in space-time, detectable by observatories here on Earth. These events help validate Einstein's theory of general relativity and open up new avenues for understanding the formation of heavy elements like gold and platinum in the universe. Each discovery brings us one step closer to understanding the very fabric of matter and its behavior under the most extreme conditions imaginable. These findings contribute to a broader, more nuanced picture of the cosmos, one that is as perplexing as it is awe-inspiring. Further out in the cosmos, a distant exoplanet, WASP 121b, has captured the attention of astronomers due to its extreme and unusual characteristics. Located about 900 light-years away from Earth, this planet belongs to a category known as hot Jupiters, a type of gas giant that orbits very close to its star. The proximity to its star results in a temperature that can soar to more than 2,000 degrees Fahrenheit, creating a hostile yet scientifically rich environment. The atmosphere of WASP 121b is not only extraordinarily hot, but also contains heavy metals like iron and magnesium that vaporize in the planet's intense heat. This phenomenon provides a unique opportunity for scientists to study how these elements behave at such extreme temperatures. The evaporation of metals and the circulation of the atmosphere could lead to the formation of clouds and winds composed of these metals, an entirely new and fascinating process that challenges our understanding of atmospheric science. In addition to its scorching temperature, WASP 121b's rapid orbit adds another layer of intrigue. The planet completes one orbit around its star every 34 hours, resulting in an incredibly swift day-night cycle. This rapid rotation causes dramatic temperature differences between the day side and the night side of the planet, offering scientists a living laboratory to study heat distribution on a world with such extreme conditions. The pronounced variation in temperature presents a perfect scenario for investigating how heat travels and redistributes across a planet's atmosphere, offering valuable insights into climate and weather patterns. With modern telescopes, scientists can closely examine the planet's atmosphere that passes the light during transits across its host star. These observations provide crucial data on the planet's atmospheric composition, temperature, and escape processes, which not only enhance our knowledge of WASP 121b itself, but also contribute to a broader understanding of the diverse exoplanets that exist beyond our solar system. In the realm of cosmology, the theory of cosmic inflation offers an explanation for the universe's early, rapid expansion. According to this theory, the universe underwent an extraordinary growth spurt shortly after the Big Bang, expanding exponentially in a fraction of a second. This event is believed to have occurred around 10 to the power of negative 36 seconds after the universe began, a tiny fraction of time in the grand scale of cosmic history. During this brief period, the universe expanded faster than the speed of light, smoothing out any irregularities and leading to the remarkably uniform cosmic landscape we observe today. Inflation theory provides a compelling answer to the question of why the universe appears so homogeneous across vast distances, and it continues to shape our understanding of the universe's origins and evolution. As the universe began to stretch, regions that were once in close proximity to one another became increasingly distant, and this grand expansion played a critical role in shaping the cosmos as we know it. This rapid inflationary process helped eliminate temperature and density variations that might have otherwise marred the uniformity of the universe. When we observe the cosmic microwave background radiation, the faint afterglow of the Big Bang, we are met with a stunningly even distribution of temperature across the sky. This homogeneous distribution is something that the theory of inflation elegantly explains. Beyond simply accounting for uniformity, inflation also offers key insights into the very structure of the universe itself. During this period of intense growth, tiny quantum fluctuations occurred, minute irregularities in the fabric of space-time. These fluctuations, which were initially imperceptible, are now thought to have seeded the formation of galaxies, star systems, and the vast cosmic structures we observe today. As the universe expanded, these fluctuations carried with them slight irregularities, and these variations gradually evolved into the cosmic web of galaxies, clusters, and vast voids that span the universe. Inflationary theory doesn't merely describe a period of rapid expansion, it serves as the framework that allows us to understand the underlying uniformity and complexity of the universe. The theory paints a picture of a universe that was once incredibly hot and dense, yet through a brief but spectacular burst of growth, it settled into the relatively calm and uniform cosmos we observe today. This shift from an almost chaotic dense state to the expansive universe we inhabit speaks to the power of inflation in shaping not only the geometry of space, but also the larger, intricate patterns of matter that form the very structure of the universe. Yet, the multiverse theory offers an entirely different perspective on reality. It challenges our fundamental understanding of the universe by proposing that what we perceive as the universe may only be one of an infinite number of potential realities. Imagine standing at the edge of a vast beach, staring out at an endless horizon. Each grain of sand, as far as the eye can see, represents a different universe, each with its own set of physical laws, dimensions, and histories. This notion suggests that our own reality is but a small fragment of a vastly larger cosmic tapestry, radically altering our perception of space, time, and existence itself. Traditionally, we have envisioned the universe as a single, closed entity, one that began with the Big Bang around 14 billion years ago. However, the multiverse theory posits the existence of other swallowing worlds, realms beyond our observable universe, which may have arisen from the same processes that birthed our own cosmic bubble. In certain models, these universes could be starkly different from one another, leading to the possibility that life or forms of existence could exist in entirely different conditions, or even in alternate versions of reality. This radical shift in perspective challenges the uniqueness of our universe, suggesting that the series of events that led to Earth and to life as we know it might just be one of an infinite set of possibilities. Whether it's alternate versions of ourselves or completely different forms of consciousness, the multiverse theory encourages us to consider an ever-expanding web of realities, each potentially filled with its own set of rules and characteristics. Such a theory raises deep philosophical questions too. If infinite versions of reality exist, what does that imply about our own significance? Do we matter in a universe teeming with countless other variations of existence? The multiverse not only entices scientists with its complex possibilities, but also compels us to reflect on our place in this boundless cosmic network. As our understanding of reality expands, we are left to ponder profound concepts such as fate, free will, and the very nature of existence itself. In this light, the multiverse invites us to explore both the physical universe beyond our reach and the deeper metaphysical questions that have eluded humanity for centuries. In a similar vein, string theory represents a monumental shift in how we think about the building blocks of the universe. At its core, string theory challenges the traditional understanding of matter, suggesting that instead of point-like particles, the most fundamental components of the universe are actually tiny, vibrating strings. These strings can vibrate in different modes, much like the strings of a musical instrument. The different vibrational patterns give rise to the properties of particles, such as their mass and electric charge. One of string theory's most profound implications is its potential to unify all of nature's fundamental forces. Currently, physics relies on separate frameworks to describe the forces that govern the universe. Quantum mechanics for the microscopic world of particles, and general relativity for the macroscopic world of gravity. String theory proposes that all of these forces, including gravity, could emerge from the same underlying framework of vibrating strings. In doing so, it brings us closer to a unified theory of everything, a single, comprehensive framework that might explain how the universe operates at its most fundamental level. String theory also introduces the idea of extra dimensions. While we are familiar with the three spatial dimensions of length, width, and height, along with the dimension of time, string theory suggests there could be additional hidden dimensions that are compacted so tightly that we cannot perceive them in our everyday lives. These extra dimensions may help explain why gravity is so weak compared to the other fundamental forces. It may be spreading out across these additional dimensions, diminishing its effect in the reality we experience. Although string theory remains a work in progress, it continues to spark exciting ideas and challenges the existing paradigms of physics, inspiring deeper exploration into the very nature of space, time, and reality itself. Another intriguing concept that has captured the imagination of both scientists and philosophers alike is the simulation hypothesis. This theory suggests that the reality we experience might not be real in the traditional sense, but rather a sophisticated simulation created by an advanced civilization. In this scenario, an advanced technological society could build simulations so complex and immersive that the entities within them, like ourselves, would be entirely unaware of their artificial nature. If this idea holds any weight, it raises profound questions about the nature of consciousness, perception, and the very fabric of existence. Consider a future where technological progress enables the creation of virtual worlds so lifelike that distinguishing them from reality would be nearly impossible. In such a world, if simulations could be created in infinite numbers, it follows that we might very well be living in one of them. This suggests that every thought, feeling, and interaction could be the product of a meticulously designed program, leaving us to question whether our lives have any inherent meaning beyond the predetermined experiences we live. This hypothesis blurs the line between creator and creation, inviting us to reconsider the roles of both the designers of our universe and ourselves as its inhabitants. If we are part of a simulation, our entire experience of reality might be governed by algorithms and predetermined scripts, forcing us to reconsider the concepts of free will and personal agency. The simulation hypothesis raises important philosophical questions that go beyond mere curiosity. It challenges our deepest assumptions about the nature of existence, pushing us to reflect on who we are, why we exist, and what lies beyond the reality we think we know. If we are indeed living in a simulation, it could indicate that there is a deeper truth underlying our universe, one that transcends our perception of it. This theory not only raises questions about our personal place in the universe, but also invites us to explore the unknown layers of reality that lie just beyond our grasp. Finally, the anthropic principle in cosmology offers an intriguing explanation for why the universe seems so finely tuned to support life. This principle suggests that the physical constants and laws of nature are not random, but rather are perfectly calibrated to allow for the existence of life as we know it. When we observe the universe, we find that even the slightest variation in fundamental forces like gravity or electromagnetism would render life as we understand it impossible. This fine-tuning raises fascinating philosophical questions. If the universe appears so exquisitely designed for life, does that imply a purposeful intent behind its creation? Are we merely the result of chance, or is there something more profound at work? As we contemplate the anthropic principle, we are left with the profound realization that we may live in a universe that, against all odds, is perfectly suited for the emergence of life, leading us to wonder whether our existence holds more significance than we could ever fully understand. However, the anthropic principle has faced its share of criticism, with some scholars arguing that it is not a robust framework for understanding the universe. One of the key points of contention is that it can lead to a form of selection bias. In essence, this criticism suggests that we may only be observing those universes that are capable of supporting life, universes like ours, where the conditions are just right for life to emerge. Critics claim that this observation could be fundamentally flawed because it stems from our very existence. After all, if we exist in this universe and are able to observe it, isn't it simply a coincidence that the universe is conducive to life? This view raises a challenging philosophical question. If every conceivable variation of the universe exists somewhere, then isn't it possible that the conditions required for life are purely incidental? This perspective casts doubt on the validity of the anthropic principle, as it could undermine scientific inquiry. Instead of pushing us toward a deeper understanding of the universe, it might limit our curiosity, compelling us to accept that we find ourselves in a life-permitting universe as just a random occurrence. Such a viewpoint risks overlooking the potential for more fundamental explanations that could explain why the constants of nature take the exact values that they do. Critics argue that the anthropic principle may, in some cases, reduce cosmology to a mere observation of our existence, rather than an explanatory framework that delves into the mysteries of why things are the way they are. Rather than pushing the boundaries of our understanding, it could create an illusion of explanation without really addressing the underlying questions. For many scientists, this represents a troubling trend, one that could limit the scope of cosmology to only what we can observe without exploring the deeper causes behind these phenomena. The debate surrounding the anthropic principle, therefore, taps into a broader philosophical discussion within cosmology about what truly constitutes a scientific explanation. Does our ability to observe and question the universe give meaning to our existence, or is it simply a byproduct of cosmic happenstance? Regardless of where one stands on this issue, the anthropic principle has sparked rich dialogue in the scientific community, urging both skeptics and advocates to ponder not only the physical laws of the universe, but also the profound significance of our very ability to comprehend them. Turning to another mind-bending phenomenon, time dilation offers a captivating insight into the nature of time itself, especially when explored within the context of strong gravitational fields, such as those surrounding black holes. Time dilation, rooted in Einstein's theory of relativity, tells us that time does not pass uniformly everywhere in the universe. When you move through the cosmos, time flows differently depending on the strength of the gravitational forces at play. Nowhere is this more evident than near a black hole, where the force of gravity is so intense that it bends not just space, but also time. Imagine this. You and a friend set out at the same moment to explore the universe. While you venture closer to a black hole, your friend stays far away in the relative safety of less intense gravity. From your friend's perspective, they would observe your movements slowing down as you approach the black hole. This happens because, for you, time is stretching out as the black hole's gravity affects you more strongly. While you might experience hours or even days passing, your friend would see what seems like an eternity unfold before their eyes. The deeper you travel into the black hole's gravitational grip, the more pronounced this time stretching becomes. At the event horizon, the critical boundary around a black hole where nothing, not even light, can escape, the difference between your experience and your friend's perception becomes extreme. As you approach this point, from your friend's vantage point, you would appear to freeze in time. But from your own perspective, you would continue your journey into the black hole, unaware of the profound difference in the passage of time that is unfolding for your friend. This stretching of time challenges everything we think we know about the flow of time. It introduces a reality where two observers, linked by the fabric of space and time, can experience time in radically different ways. Time dilation at black holes not only deepens our connection with the universe, but also forces us to grapple with the very nature of time and space. What does it mean for time to behave in such an odd and unpredictable way? And how do we reconcile this with our everyday experiences of time? This brings us to the quantum foam hypothesis, which explores the universe at its most minuscule scale, offering a peek into the very structure of space-time. The quantum foam idea imagines that, at the smallest possible level, space-time is far from smooth. In fact, it's a chaotic, turbulent froth, similar to the bubbling surface of a pot of boiling water. Far from being a serene, unchanging backdrop for cosmic events, space-time at these incredibly small scales is an active, dynamic entity, constantly fluctuating and changing. This theory hinges on the principles of quantum mechanics, which are known for their inherent uncertainty and unpredictability. In this framework, pairs of particles can spontaneously appear and disappear in the vacuum of space, creating a frothy, ever-changing structure. If space-time behaves in such a chaotic manner, it fundamentally alters our understanding of the universe. Instead of viewing space-time as a stable, unchanging stage for events, the quantum foam suggests that even the fabric of the cosmos is influenced by the same quantum fluctuations that govern the behavior of particles. The implications of this idea are far-reaching. If quantum foam is indeed the true nature of space-time, it could revolutionize our understanding of gravity, time, and space. It suggests that the very essence of the universe might be shaped by quantum effects, offering a potential bridge between the worlds of quantum mechanics and general relativity. If quantum foam can reconcile the behavior of the very small with the very large, it might offer a unified theory of everything, something that has eluded physicists for decades. This fascinating concept challenges traditional views of the universe, pushing us to think beyond our conventional understanding of space, time, and reality itself. It suggests that at the most fundamental level, the universe is far more mysterious and dynamic than we could have ever imagined. The concept of quantum foam offers an intriguing possibility for understanding the origins of the universe. If space-time was once dominated by this chaotic and fluctuating foam, it raises profound questions about the very birth of cosmic structures. What role did these minute fluctuations play in the formation of galaxies, stars, and other celestial bodies? Could the quantum foam have been the primordial foundation from which the universe's structures emerged, influencing their development in subtle and unpredictable ways? This hypothesis invites us to reconsider everything we know about the cosmos, challenging our understanding of the forces that shaped it. As scientists delve deeper into the mysteries of quantum mechanics and cosmology, the quantum foam remains a captivating subject of exploration, offering new insights into the most fundamental aspects of the universe's creation. In the realm of galaxies, irregular ones stand out as some of the most fascinating celestial objects, defying traditional classification with their lack of symmetry and structure. Unlike the orderly spiral and elliptical galaxies, which possess clearly defined shapes and organized star systems, irregular galaxies appear chaotic, unpredictable, and disordered. This absence of structure might make them difficult to categorize, but it is precisely this quality that lends them a unique allure. Irregular galaxies challenge the conventional expectations of how galaxies should look and behave, highlighting the diverse and dynamic nature of the universe. One of the most striking characteristics of irregular galaxies is their rich content of gas and dust, which is far more abundant than in their spiral or elliptical counterparts. This excess of material acts as a fertile ground for ongoing star formation, creating vibrant clusters of young, hot stars. These galaxies can appear in a kaleidoscope of colors, as new stars are born amid clouds of gas, their light reflecting off the surrounding dust. The contrast with the older, more subdued populations of stars in elliptical galaxies, or the more structured star systems of spiral galaxies, is stark. While elliptical galaxies tend to feature older, cooler stars with a more reddish hue, irregular galaxies are alive with youthful, blue-tinged stars that inject energy and color into their surroundings. The size and scale of irregular galaxies add another layer of complexity to their nature. They vary widely in size, ranging from small, compact dwarf galaxies to sprawling giants that contain billions of stars. This variability allows them to interact in ways that spiral and elliptical galaxies cannot. Irregular galaxies frequently undergo collisions and mergers, their chaotic nature making them more susceptible to gravitational interactions. These interactions can lead to further star formation, the blending of stellar populations, and the reorganization of their structures. In some cases, this can lead to the creation of new, temporary forms of order, only to be disrupted again by another cosmic collision. This dynamic process underscores the ongoing evolution of galaxies and the interplay between order and chaos in the universe. Studying irregular galaxies offers a window into the mechanisms of galaxy formation and evolution. They serve as living examples of how galaxies can evolve, driven by the intricate dance of gravity, gas, and dust. Each galaxy, regardless of its shape, plays a crucial role in the grand narrative of the universe, contributing to the broader understanding of cosmic development. The interplay of forces that shape these galaxies is a reminder of the delicate balance between chaos and order that governs the universe. It is in this balance that the beauty of the cosmos resides, offering a spectacle for all who gaze upon the night sky. One of the most captivating cosmic events in the future of our galaxy is the impending collision between the Andromeda Galaxy and the Milky Way. These two massive, star-filled galaxies are on a collision course, traveling toward each other at a velocity of about 250,000 miles per hour. While this may seem like an inevitable disaster, it is not a cataclysmic crash, but rather a complex cosmic dance. Over the course of several billion years, the gravitational forces between the two galaxies will interact, pulling and stretching their stars, gas, and dust in intricate ways. The stars themselves, however, are so widely spaced that direct collisions between them are unlikely. Instead, the interaction will trigger bursts of new star formation as the gas and dust clouds within each galaxy collide and compress. As Andromeda and the Milky Way draw closer, their gravitational pull will reshape each galaxy's structure, eventually leading to a merger. The result of this galactic union will be a much larger elliptical galaxy, some scientists humorously referring to it as Melam, a combination of both galaxy names. This process, though spanning billions of years, offers a rare opportunity to witness how galaxies evolve and interact, and it serves as a microcosm of the larger cosmic processes that govern galaxy formation and destruction. The gravitational forces at play will not only affect the stars, but also the dark matter within both galaxies. The collision could potentially rearrange the dark matter, changing its distribution and influencing the dynamics of the new galaxy in ways that are still largely unknown. While this grand collision is too far in the future for humans to witness in our lifetimes, the inevitable transformation of the Milky Way and Andromeda is a profound reminder of the constantly changing nature of the universe. The same forces that shape these galaxies into their current forms will continue to mold them into something entirely new, demonstrating the cyclical and ever-evolving nature of cosmic evolution. The dynamics of this collision echo throughout the universe, as countless other galaxies have undergone or will undergo similar transformations. Looking at the Sombrero galaxy, also known as Messier 104, we encounter another striking example of a galaxy with a rich history and complex structure. Located about 30 million light-years from Earth, the Sombrero galaxy's name is derived from its resemblance to a wide-brimmed hat. It stands out for its bright core and prominent dust lanes, features that have made it a focal point for astronomers studying galaxy formation. The Sombrero galaxy's impressive bulge, which contains a large population of old stars, suggests a history of mergers and interactions with other galaxies. This bulge, along with the well-defined disk structure, provides vital clues about the processes that shape and evolve galaxies over time. By studying the Sombrero galaxy, scientists gain important insights into the mechanisms that drive galaxy formation. The galaxy's long history of gravitational interactions offers a glimpse into how galaxies evolve, both in terms of their physical structure and the stellar populations they host. Through these observations, astronomers are uncovering the complex forces that govern the formation and growth of galaxies, piecing together the story of the universe's ongoing evolution. In every corner of the universe, galaxies are constantly evolving, their structures shifting in response to the gravitational forces that govern their movements. Whether it's the chaotic beauty of irregular galaxies, the graceful dance of a galactic collision, or the ancient history captured in the light of a distant spiral galaxy, each of these cosmic phenomena adds a chapter to the ongoing story of the universe. The study of galaxies, from the smallest dwarf galaxies to the largest galactic mergers, not only enhances our understanding of the cosmos, but also reminds us of the incredible complexity and beauty that exists in the universe, waiting to be discovered. The Sombrero galaxy, one of the most fascinating cosmic structures in our universe, is home to an active supermassive black hole at its very core. This black hole, surrounded by a rich tapestry of stars, gas, and dust, sheds light on the intricate relationship between black holes and the evolution of galaxies. The influence of such a powerful black hole on its host galaxy offers a critical perspective on how galaxies evolve and grow over billions of years. It underscores the complex interplay between the central black hole and the surrounding materials, which in turn can have profound effects on star formation. By observing the Sombrero galaxy, astronomers gain not only essential facts and measurements, but also a deeper understanding of these cosmic processes, highlighting how galaxies are shaped and transformed throughout time. The Sombrero galaxy, with its distinctive structure, functions almost like a cosmic laboratory. Here, astronomers can investigate various stages of galaxy formation and the mechanisms at work behind their evolution. The insights gained from such studies are not limited to this one galaxy. In fact, they have broader implications, shaping our understanding of the universe as a whole. This unique galaxy allows scientists to peer into the heart of galactic evolution, shedding light on the forces that drive the cosmos. As we continue to observe the Sombrero galaxy, we unravel more of the universe's mysteries, adding pieces to the vast puzzle of cosmic history. Another galaxy that provides a wealth of insights is NGC 1277, located around 60 million light-years away in the constellation of Perseus. This galaxy, also known as the PEUL galaxy, stands out due to its unusual features, especially its supermassive black hole. At more than 14 billion times the mass of our Sun, this black hole is truly extraordinary, accounting for about 75% of the total mass of the entire galaxy. This disproportionality challenges the long-held assumptions about the relationship between the mass of a galaxy and that of its central black hole. Traditionally, astronomers have believed in a relatively stable connection between the mass of a galaxy and its supermassive black hole. Larger galaxies typically harbor larger black holes, with a corresponding mass of stars and gas. However, NGC 1277 defies this trend. Instead of a galaxy brimming with stars and gas, NGC 1277 appears to have been stripped of much of its surrounding material, leaving behind a compact structure dominated almost entirely by its supermassive black hole. This anomaly challenges our understanding of galactic evolution and raises crucial questions about the development of supermassive black holes. Could these colossal black holes evolve independently of their host galaxies? And if so, what factors might influence such growth, allowing a black hole to reach a size far out of proportion to its host galaxy? NGC 1277, in its puzzling nature, suggests that there might be pathways for black hole growth that we have yet to fully understand, prompting scientists to rethink existing models of galactic formation and black hole evolution. As we continue to study NGC 1277, we are compelled to reconsider the accepted theories about the processes governing both galaxies and black holes. This strange galaxy serves as a key to unlocking deeper truths about the universe and our understanding of its complexities, forcing astronomers to explore new avenues of research and potentially reshape our views on cosmic evolution. Meanwhile, the Whirlpool galaxy, located about 23 million light-years away, offers another extraordinary case for study. Known for its striking spiral arms and a bright active center, the Whirlpool galaxy serves as a prime example of a spiral galaxy. Its vast clouds of gas and dust are the raw materials from which new stars are born. By closely observing the Whirlpool galaxy, astronomers gain invaluable insights into the process of star formation, as well as the dynamic interactions between stars, gas, and dust. One of the most significant features of the Whirlpool galaxy is the active star formation occurring in its spiral arms. These regions are dense with molecular clouds, clumps of gas and dust that collapse under their own gravity to form new stars. By observing these processes, scientists can learn about the conditions that foster star formation, including the temperature, density, and turbulence within these clouds. This allows them to piece together the intricate conditions under which stars come to life. Moreover, the Whirlpool galaxy provides a fascinating opportunity to witness the full life cycle of stars. Some stars in the galaxy are still in their infancy, while others have reached their peak and are burning brightly. Through high-resolution imaging and spectroscopy, astronomers can closely examine how these stars emit light and interact with the gas and dust around them. This interaction influences the molecular clouds, further fueling the formation of new stars and creating a vibrant, ever-changing ecosystem within the galaxy. The study of the Whirlpool galaxy is like a living narrative of the life cycle of stars set against the broader backdrop of cosmic evolution. Each new observation contributes to our understanding of the birth, life, and death of stars. As we explore these processes, we gain deeper insights not only into the workings of the Whirlpool galaxy, but also into the fundamental nature of galaxies across the universe. The story of star formation in the Whirlpool galaxy illuminates the broader cosmic narrative, offering a rare window into one of the universe's most magnificent and essential processes. In addition to these remarkable galaxies, the study of active galactic nuclei (AGN) reveals some of the most awe-inspiring phenomena in the cosmos. These incredibly energetic centers are found in certain galaxies, where a supermassive black hole resides at the core. As matter spirals into these black holes, it releases vast amounts of energy in the form of radiation and high-speed particle jets, making AGN some of the most luminous and powerful objects in the universe. The energy emitted by AGNs can sometimes surpass the total luminosity of the entire host galaxy. This variation in brightness, ranging from a few times the luminosity of the Sun to millions of times greater, provides crucial clues about the physical processes occurring at the heart of these galaxies. By studying the light emitted by AGNs, astronomers can learn more about the dynamics of matter falling into black holes, the interactions between this matter and the surrounding gas, and the intricate dance of energy and matter that unfolds in these energetic environments. Different types of AGNs, such as quasars and blazars, offer unique insights into the nature of these powerful cosmic phenomena. Each type of AGN provides a different perspective on the extreme conditions at the centers of galaxies and contributes to our broader understanding of the universe. By studying these active galactic nuclei, astronomers are able to unlock the secrets of some of the most energetic and mysterious objects in the cosmos, helping to illuminate the complex processes that govern the behavior of galaxies and the universe itself. Through the study of galaxies like the Sombrero, NGC 1277, the Whirlpool, and the fascinating phenomena of active galactic nuclei, we continue to expand our knowledge of the cosmos. Each discovery offers new pieces of the puzzle, bringing us ever closer to understanding the vast and dynamic universe in which we live. Astronomical objects known as active galactic nuclei, AGNs, serve as extraordinary beacons, shedding light on distant galaxies that might otherwise remain obscured by the vast curtain of cosmic dust. By carefully analyzing the light emitted from AGNs, astronomers are able to extract a wealth of information about galaxies that lie far beyond our own. These beacons offer critical data on the composition, distance, and evolution of far-flung galaxies, allowing researchers to peer deep into the heart of the cosmos. The energy emitted by AGNs holds many secrets, revealing the presence of heavy elements, the velocity of material being ejected at unimaginable speeds, and even offering glimpses into the intricate structure of the host galaxies themselves. This multidimensional view provides scientists with a comprehensive understanding of the galaxy's histories, allowing them to trace their development through cosmic time. Moreover, studying the energy output of AGNs enriches our understanding of the very conditions that prevailed in the early universe. These energetic phenomena help illuminate the role supermassive black holes play in the formation and ongoing evolution of galaxies. Over the span of billions of years, galaxies undergo profound transformations, and the study of AGNs provides the essential context in understanding how central black holes exert influence over the surrounding stellar populations. Active galactic nuclei are not just awe-inspiring celestial features. They are essential to unlocking the deeper mysteries of galaxy behavior and the fundamental mechanisms that drive the universe itself. In parallel with AGNs, barred spiral galaxies present another fascinating realm of cosmic investigation. These galaxies, such as our Milky Way, exhibit a unique and visually striking bar-like structure that stretches outward from their central bulges. The distinctive shape of barred spirals has long captivated astronomers, but the formation of these bars remains one of the greatest puzzles in galactic science. Why do they form, and what conditions lead to the creation of these features in the first place? Answering these questions will shed light on the underlying forces that shape galactic dynamics. By understanding the formation of these bars, scientists gain insights into the internal mechanics of galaxies and the broader processes that govern their evolution. One particularly intriguing aspect of barred spiral galaxies is the potential role of dark matter in their formation and development. It is widely believed that the gravitational influence of dark matter has a profound impact on the formation, stabilization, and even dissolution of a galaxy's bar structure. The relationship between dark matter and the bar is far from straightforward, and much remains unknown. Some theories suggest that the specific distribution of dark matter within a galaxy can either stabilize the bar structure, allowing it to persist, or cause it to gradually dissipate over time. Unraveling this complex relationship could offer crucial insights into the nature of dark matter itself and its profound influence on the behavior of galaxies across the cosmos. Additionally, the life cycle of these galactic bars presents another captivating mystery. Bars are not permanent fixtures within galaxies. Over time, they can weaken, evolve, or even dissolve entirely due to a variety of internal and external influences. This raises compelling questions about the fate of the stars, airs, and gas that were originally concentrated within the bar structure. As the bar fades away, do these stars reintegrate into the galaxy's main disk, or do they shift into new orbits entirely? Observations suggest that the dynamics within barred galaxies are significantly shaped by the presence of the bar itself. The structure of the bar can impact everything from star formation rates to the overall layout of the galaxy, illustrating the profound influence that galactic features have on their larger scale evolution. The complex interactions between the bar structure, the forces of dark matter, and the evolving life cycle of stars within these galaxies continue to captivate scientists. Each new discovery in this field opens the door to deeper questions, pushing the boundaries of our understanding of the cosmos. With the study of barred spiral galaxies, we are not merely learning about a peculiar feature of certain galaxies. We are uncovering fundamental truths about the forces that shape the universe, and perhaps even the very nature of space and time itself. The role of bars in spiral galaxies, particularly in their ability to influence the fate of these cosmic entities, has become an increasingly intriguing subject for astronomers. Recent studies have revealed a fascinating trend. Barred spiral galaxies appear to be more efficient at forming new stars than their non-barred counterparts. This discovery suggests a possible connection between the evolutionary processes of the galactic bars and the overall life cycle of a galaxy. Understanding the mechanics behind these celestial features could unlock significant insights into not only the barred galaxies themselves, but also the broader nature of galaxies scattered across the universe. This could ultimately deepen our understanding of the dynamic forces that influence and shape the vast structures of the cosmos over time, offering a clearer view of the intricate cosmic dance that has unfolded for billions of years. In a similar vein, the dwarf planet Eris, nestled within the scattered disk region of our solar system, stands as one of the more captivating discoveries made in recent astronomical history. Although Eris is slightly smaller than Pluto, it possesses a remarkable characteristic that makes it stand out: its mass. Eris is more massive than Pluto, weighing in at nearly 1.5 times the mass of our well-known planetary neighbor. This realization has prompted astronomers to reconsider how we classify the distant objects in the outer reaches of our solar system. Eris orbits the Sun at a distance more than 3 times that of Pluto, requiring a staggering 557 Earth years to complete one full orbit. What further sets Eris apart is its highly eccentric and inclined orbit, which carries it far from the plane of the solar system. This means that its path is more erratic and tilted in comparison to the more predictable orbits of other celestial bodies in our cosmic neighborhood. Eris's surface is composed predominantly of ice and rock, with a layer of frozen methane coating its exterior. This icy shell gives Eris a strikingly bright appearance as it reflects the light of the sun. One of the most telling features of Eris is its small moon, dysnomia. Observing the moon's orbit has allowed scientists to precisely calculate the mass of Eris, cementing its place as one of the largest known dwarf planets. The relationship between Eris and dysnomia also highlights an important aspect of the dynamics surrounding dwarf planets. By studying the gravitational interactions between these two bodies, scientists are gaining a better understanding of the processes that govern the formation and evolution of planetary bodies in distant, frigid parts of the solar system. This discovery is particularly noteworthy given the ongoing debate about Pluto's status as a planet. The existence of Eris forces a re-evaluation of the definitions and boundaries traditionally assigned to celestial bodies within our solar system. Eris broadens the scope of our understanding, reminding us that the universe is populated with a much greater diversity of objects than the traditional 8-planet model suggests. The presence of Eris encourages us to expand our view of the solar system and reinforces the notion that there is much more to be explored beyond our familiar planetary neighbors. The idea of ocean worlds has garnered increasing interest in recent years, particularly with regard to moons such as Europa and Enceladus. These moons, which orbit Jupiter and Saturn respectively, have become focal points for scientific inquiry due to the compelling evidence suggesting that they harbor subsurface oceans beneath their icy crusts. The potential existence of these vast hidden oceans opens up intriguing possibilities about the potential for life beyond Earth. Europa, for example, is thought to have an ice crust that floats atop a deep ocean. The interaction between this ocean and Europa's rocky mantle could create the necessary chemical reactions to support life, potentially on a scale we've never previously imagined. It's hypothesized that Europa's ocean may contain more water than all of Earth's oceans combined. This realization has profound implications for our understanding of where life could exist in the universe, suggesting that life might be able to thrive in environments we once considered inhospitable. Enceladus tells a similar story. Observations from NASA's Cassini spacecraft have revealed geysers of water vapor erupting from its surface, indicating the presence of an ocean beneath. Even more striking, the plumes contain organic compounds, the building blocks of life. This finding further complicates our understanding of where life might exist beyond Earth and fuels the ongoing search for extraterrestrial life. The exploration of these ocean worlds not only offers exciting possibilities for astrobiology, but also enhances our understanding of the diverse environments in our solar system. By studying moons like Europa and Enceladus, we gain insights into the complex processes that govern ocean dynamics, crust formation, and perhaps even the conditions that might be conducive to life. The concept of ocean worlds challenges us to reconsider how we search for life and encourages scientists to look at other celestial bodies in new and innovative ways. Beyond our solar system, the discovery of exoplanets continues to expand the frontiers of human knowledge. One of the most fascinating exoplanets is HD 189733b, a gas giant located approximately 63 light-years from Earth. HD 189733b has earned a reputation for its extreme and often violent weather patterns. Atmospheric temperatures on this planet soar to around 1,000 degrees Celsius, and winds can reach speeds of up to 2,000 kilometers per hour. These extreme conditions make the planet an ideal laboratory for studying atmospheric dynamics under hostile environments. HD 189733b's deep blue hue, caused by the presence of silicate particles in its atmosphere, suggests a cloud structure far more complex than anything observed in our solar system. Observations have also revealed violent storms, further adding to the intrigue surrounding this distant planet. Additionally, scientists have detected signs of water vapor in the planet's atmosphere, suggesting that water could play a role in its atmospheric processes. This exoplanet offers a unique opportunity to test our understanding of how planetary atmospheres function under extreme conditions of heat, pressure, and turbulence. By studying HD 189733b, astronomers can refine their models of atmospheric behavior, deepening our understanding of how exoplanets may evolve in environments vastly different from our own. Insights gleaned from this distant world challenge our preconceived notions about planetary atmospheres and open the door to a broader understanding of the complex and varied conditions that exist throughout the universe. The extreme temperatures and powerful high-speed winds on HD 18973b serve as a unique laboratory for scientists, pushing the boundaries of existing atmospheric models. This alien world, located light-years away, presents conditions so intense that they challenge our understanding of atmospheric behavior. These extreme elements, raging storms, searing heat, and relentless winds, offer researchers the rare opportunity to study how such forces shape weather patterns, influence cloud formation, and even alter the chemical makeup of an atmosphere. Such investigations deepen our comprehension of what might be found on other distant exoplanets, including those that could potentially support life. What makes HD 18973b particularly captivating is its ability to expand our knowledge about the wide variety of possible atmospheric conditions on distant worlds. These extreme environments, though hostile, are incredibly informative. They not only show us the extremes that planets can endure, but also provide insights into how atmospheres might behave under similarly severe circumstances on other exoplanets. By examining these conditions, scientists are able to identify which features could make a planet more or less hospitable to life. This exploration could one day help pinpoint exoplanets with environments that might support human life, or at least some form of life, in the far reaches of the universe. Exoplanets like HD 18973b push the boundaries of what we thought possible, offering invaluable lessons in planetary science. Their existence demonstrates the vast diversity of conditions that can arise on planets, helping scientists refine the parameters of habitability across the cosmos. These findings continue to encourage research that could shape our understanding of planetary formation, atmospheric dynamics, and life itself in ways we never imagined. Another exciting area of exploration lies in the Trappist-1 system, where an extraordinary discovery has unfolded. Just over 40 light-years from Earth, this star system is home to 7 Earth-sized planets, 3 of which orbit in the star's habitable zone, the region where conditions are just right for liquid water to exist on a planet's surface. Liquid water, as we know, is essential for life as we understand it, making the discovery of potentially habitable worlds here incredibly significant. What sets Trappist-1 apart is the nature of its host star, a cool dwarf star. While many stars in the universe can host planets in the habitable zone, the relatively low temperature of Trappist-1's star allows its planets to orbit much closer than those around hotter stars. This proximity means that the planets are not scorched by excessive heat, creating a much more favorable environment for water to exist on their surfaces. For scientists, this is a tantalizing prospect. Could these planets harbor the conditions necessary for life? The answer may lie in the atmospheres of these worlds, which may contain gases like oxygen and methane, substances linked to biological processes here on Earth. Astronomers are already using powerful telescopes to study the light that passes through the atmospheres of these planets during transits. By analyzing the chemical signatures in this light, they hope to detect subtle hints of life, or at least the conditions that might support it. These chemical signals, if identified, could dramatically transform our understanding of habitability, expanding the possibilities of life beyond Earth in ways that could change the course of human history. Yet the discoveries don't stop there. The Trappist-1 system raises further questions about planetary dynamics. With so many planets packed into such a small space, there is a significant chance that their gravitational interactions could influence each other's atmospheres and climates. These interactions might create a rich variety of environments, each with its own potential for supporting life. As the data continues to come in, the Trappist-1 system stands out as one of the most exciting areas for astrobiological research. The complexity of this system hints at the vast array of possibilities waiting to be uncovered, making it a focal point for scientists searching for life beyond our solar system. In parallel, the discovery of super-Earths is reshaping our understanding of planetary systems and challenging the very way we classify planets. Traditionally, planets were categorized by size, either as terrestrial worlds like Earth and Mars or gas giants like Jupiter and Saturn. But the discovery of super-Earths, which are planets that have a mass greater than Earth's, usually between 1 and 10 times Earth's mass, complicates this classification. Super-Earths are intriguing because, despite their larger mass, they often retain solid surfaces and rocky compositions, and some may even possess atmospheres. These characteristics suggest that there are more types of planets out there than we initially thought, planets that fall somewhere between the two classic categories of rocky worlds and gas giants. This new category of super-Earths opens up exciting possibilities for habitability. For example, a super-Earth might have a thick atmosphere capable of trapping heat and maintaining liquid water on its surface, potentially making it suitable for life. The implications of these discoveries challenge existing theories about how planets form and the materials that make up their structure. Super-Earths might not only alter how we categorize planets, but they also force us to reconsider the entire process of planetary formation and evolution. As more super-Earths are discovered, each new find helps refine our understanding of planetary systems. These discoveries push the boundaries of what we know about planetary compositions, orbital mechanics, and the range of conditions that might support life. The implications go far beyond academic classifications. They open the door to new possibilities for understanding where life could thrive in the cosmos. For scientists, these findings are as much about understanding the variety of planetary environments as they are about imagining the life that could emerge in such diverse conditions. In a similar vein, the discovery of liquid water on Mars has had profound implications for our understanding of the planet's geological history. For years, scientists had believed that Mars was a cold, dry desert, shaped primarily by wind and erosion. The discovery of liquid water, however, challenges this perception and suggests that Mars may have once been more Earth-like than we thought, perhaps even capable of supporting life in some form. This revelation invites a rethinking of the planet's past, offering new avenues of exploration as we continue to search for signs of life and try to uncover the mysteries of Mars's geological evolution. These discoveries, whether they concern the extreme conditions of HD 129733b, the potential for life in the Trappist-1 system, or the intriguing characteristics of super-Earths, highlight the vast diversity of worlds in the universe. Each new revelation brings us closer to understanding not only where planets can exist, but how they might evolve, and ultimately, whether they can support life. These findings push the boundaries of what we know about the cosmos, inviting us to consider the possibilities that lie beyond our solar system in the vast expanse of space where life in all its forms might be waiting to be discovered. However, the evidence for liquid water on Mars reveals something truly remarkable. It suggests that there was a time in the distant past when the planet's environment was far more dynamic, possibly even habitable. This shifts our perception of Mars from being just a dead, barren world to a place that could have supported life under the right conditions. The presence of liquid water is a powerful agent of change. Water in any landscape has the ability to shape terrain in profound ways, driving erosion, transporting sediment, and initiating a range of geological processes. The discovery of liquid water on Mars hints at a time when the planet experienced significant climatic variations. These shifts could have fostered the creation of rivers, lakes, and potentially even oceans. Such bodies of water would have played a key role in sculpting the surface features that we see today: vast valleys, ancient riverbeds, and sedimentary rock formations. These features serve as evidence of a wetter, more Earth-like world that may have once existed. The implications for understanding the history of Mars are nothing short of enormous. Liquid water implies that the planet's climate was far more temperate and varied than we once imagined. This challenges our previous understanding of the Martian environment, offering a glimpse into a time when the planet could have been much more hospitable. The presence of water, however, raises even more intriguing questions, particularly concerning the interaction between water and Mars's geology. The evidence suggests that Mars' subsurface might not have been as dry and arid as we once thought. Water, even in liquid form, could have influenced the development of minerals and spurred a variety of chemical reactions beneath the planet's surface. Scientists are eager to understand these interactions because they hold vital clues about the planet's evolution, its atmosphere, climate, and the potential for life. Water, as a cornerstone for life as we know it, provides tantalizing possibilities. Could microbial life have once thrived on Mars, even in its ancient past? Was there a time when life may have existed in Martian rivers or lakes? These questions are not just academic, they invite us to rethink our assumptions about life beyond Earth. If Mars had liquid water, it opens up the exciting possibility that life, in some form, might have once called Mars home. But the significance of liquid water on Mars goes beyond just geology or the prospect of ancient life. It challenges our understanding of habitability itself. What does it mean for the potential of life on other planets in our solar system or beyond? Could there be other worlds similarly shaped by liquid water that might also have the right conditions for life to emerge? This is where the story of Mars intersects with the broader narrative of life in our universe. And it is not just Mars that piques the interest of scientists. Far beyond our red neighbor, a fascinating exoplanet has captured the imaginations of astronomers and astrobiologists alike. K208b, an exoplanet located approximately 1,770 light-years away in the constellation Leo, is one of the most intriguing discoveries of recent years. About 8 times the mass of Earth, K208b resides in the habitable zone of its star, a region where conditions might be just right to allow liquid water to exist on its surface. Liquid water is, of course, a key ingredient for life as we know it, which makes K208b a prime target for study in the search for extraterrestrial life. What makes K208b particularly captivating is its atmospheric composition. Recent observations suggest the presence of water vapor in its atmosphere. This discovery has added a layer of complexity to our understanding of its habitability. Some theories propose that K208b could possess a thick atmosphere, rich in hydrogen, possibly surrounding a watery interior or even oceans. This stands in contrast to traditional models of habitability, which often rely on Earth-like conditions. Instead, the discovery of water vapor could indicate that K208b might offer a unique environment, one where life could flourish under conditions very different from those on Earth. If K218b's atmosphere includes not just water vapor but also other specific gases, it could provide the perfect setting for life forms that might not resemble anything we've encountered on our own planet. The very presence of water vapor in the atmosphere, combined with other potentially life-sustaining gases, makes K218b an exciting candidate in the search for alien life. What might these life forms look like? How could they survive and thrive in such an environment? These questions continue to fuel the curiosity of scientists, offering us a glimpse of what life beyond Earth might be like. Together, the evidence from Mars and the intriguing potential of exoplanets like K218b not only revolutionize our understanding of habitability, but also expand our search for life. Water is no longer viewed just as a fundamental element for life here on Earth. It has become the key to unlocking the mysteries of the cosmos, a signpost guiding us toward the possibility of life elsewhere in the universe. From the ancient riverbeds of Mars to the distant exoplanets that lie beyond our reach, these discoveries invite us to rethink what it means to be alive and to wonder where life might exist in the vastness of space. The study of exoplanets, particularly those like K218b, offers an exciting glimpse into the diverse environments that could potentially support life across the cosmos. K218b, located in the habitable zone of its star, raises crucial questions about the adaptability and resilience of life. It suggests that life might not be as restricted to Earth-like conditions as once assumed, thriving instead in high-pressure atmospheres with a range of chemical compositions. Such findings challenge the long-held Earth-centric view of life, urging scientists to rethink what conditions are truly necessary for life to emerge. As we explore more planets like K218b, we continue to expand the very definition of life, breaking away from terrestrial limitations. Each discovery like this enriches our understanding, sparking profound questions about the very nature of existence and the infinite variety of potential ecosystems that could exist in the universe. We are beginning to realize that life may not be confined to familiar environments, like those we find here on Earth. This evolving perspective is pushing scientists to think more broadly, considering a wider range of conditions under which life could arise. The study of distant exoplanets and the environments they harbor presents an exciting frontier in astrobiology, one where the boundaries of life are continuously being redefined. In a similarly profound way, the study of gamma-ray bursts, GRBs, unveils some of the most extreme and captivating phenomena in the universe. These brief, yet incredibly powerful, flashes of gamma radiation release more energy in a fraction of a second than the sun will emit over its entire 10 billion year lifespan. The origins of these bursts are diverse, though they are most commonly linked to the catastrophic deaths of massive stars, leading to the formation of black holes or neutron stars. The amount of energy produced in these events is so extraordinary that they become central points of interest for astronomers and astrophysicists who seek to understand the forces at play during these cosmic explosions. When a massive star reaches the end of its life and exhausts its nuclear fuel, it can no longer support itself against the immense pull of gravity. This results in a collapse of the star's core, often triggering a supernova explosion that ejects vast amounts of material at incredible speeds. In some cases, if the explosion is asymmetrical, it creates jets of material moving at nearly the speed of light. These jets produce intense gamma rays, which we observe as a gamma ray burst. On the other hand, some bursts originate from the merger of neutron stars. The collision of these dense remnants generates similar energetic jets, leading to equally awe-inspiring phenomena. The sheer intensity of these bursts can cause them to briefly outshine entire galaxies. While the duration of these bursts is typically measured in milliseconds to minutes, their brightness can be so intense that they momentarily surpass the combined luminosity of the galaxies that host them. In rare instances, gamma-ray bursts can even affect Earth's atmosphere if one were to occur in our cosmic neighborhood. Fortunately, these events are exceedingly rare, and their vast distances from us mean they pose little threat to our planet. Nonetheless, the study of gamma-ray bursts provides invaluable insights into the evolution of the universe, particularly the life cycles of stars and the extreme environments in which these phenomena occur. Gamma-ray bursts ignite a deeper appreciation for the dynamic and energetic nature of the universe, serving as cosmic reminders of the forces that shape the cosmos in ways we are only beginning to understand. They reveal the violent end of massive stars and offer glimpses into the most extreme conditions known in the universe, thus expanding our understanding of cosmic evolution and stellar life cycles. A supernova, in many ways, represents the dramatic final chapter in a star's life, marking an explosive end to its existence. This cataclysmic event takes place when a star has exhausted its nuclear fuel and can no longer withstand the crushing force of gravity. As the star collapses, its core implodes, triggering a chain of nuclear reactions that release an unfathomable amount of energy. This energy drives the outer layers of the star outward, creating one of the most spectacular phenomena in the universe. But supernovae are not just visually stunning. They play a critical role in enriching the cosmos with elements necessary for life as we know it. During the intense heat and pressure of a supernova, elements that cannot be created during the normal course of stellar life are forged. These include heavy elements like iron, gold, and even uranium, substances that would not exist in such quantities without the explosive death of a star. The outer layers ejected during the explosion carry these newly formed elements into the interstellar medium, enriching the gas and dust already scattered throughout space. Over time, these elements mix with the surrounding material, forming the building blocks for new stars, planets, and potentially even life. In essence, supernovae act as the universe's recycling centers, not only marking the end of a star's existence, but also laying the groundwork for the creation of new celestial bodies. Without the contribution of elements from supernovae, the universe would be a simpler, less complex place, lacking the diversity of elements necessary for life and complexity. Our very existence is intricately tied to the remnants of ancient supernovae, as the elements created in these explosive deaths formed the chemistry that makes up our planet and our bodies. When two neutron stars collide, the resulting event is nothing short of a cosmic spectacle. Neutron stars, the dense remnants of supernovae, pack more mass than our sun into a sphere no larger than a city. The collision of these compact stellar objects sets off an explosive chain reaction, one that produces some of the most fascinating phenomena in the universe. One of the most significant outcomes of this collision is the creation of gravitational waves, ripples in the fabric of space-time. These gravitational waves were first detected directly in 2015 by the LIGO Observatory, confirming Einstein's century-old predictions about the nature of general relativity. As neutron stars merge, they distort space-time, sending waves across the universe at the speed of light. This discovery not only confirms key aspects of our understanding of gravity and the universe, but also opens entirely new avenues of research. Gravitational waves provide us with a novel way of studying cosmic events, offering a unique perspective on some of the most violent and energetic processes in the universe. Each of these extraordinary phenomena, the study of exoplanets, gamma-ray bursts, supernovae, and neutron star collisions, provides invaluable insights into the universe's history, its evolution, and the forces that shape it. They remind us that the universe is a dynamic, ever-changing place, where even the most catastrophic events play a crucial role in the creation of new stars, planets, and perhaps even life itself. Through these discoveries, we continue to push the boundaries of our understanding, unveiling the remarkable and sometimes mind-boggling complexities of the cosmos. The violent collision of neutron stars marks one of the most awe-inspiring events in the universe, when these dense, compact remnants of collapsed stars spiral towards each other. Their merger creates conditions unlike anything seen elsewhere. The intense heat and pressure foster a process known as rapid neutron capture, or the R process, which acts like a cosmic factory. In mere moments, this process builds some of the heaviest elements in the periodic table, including gold and platinum. As the neutron stars merge, they unleash enough energy to fuel the creation of these precious metals, materials that ultimately find their way into the jewelry we wear and the electronics that power our daily lives. The very gold in a ring or platinum in a smartphone could trace its origins to the cataclysmic death of neutron stars billions of years ago. These star-shattering collisions also trigger an immense burst of gamma rays, known as a short gamma ray burst, which is one of the brightest and most powerful explosions in the universe. When two neutron stars collide, the energy released can outshine entire galaxies, flooding space with light and radiation. These bursts of energy are detectable across millions of light years, providing astronomers with an invaluable glimpse into the workings of the universe. The study of these high-energy events offers profound insights into the extreme physics at play in the cosmos, revealing the raw forces that shape the universe as we know it. In a similar vein, tidal disruption events, TDEs, provide yet another glimpse into the dynamic forces that govern celestial objects. A TDE occurs when a star ventures too close to a supermassive black hole, and the black hole's gravity overpowers the star's own gravitational pull. The result is an extraordinary spectacle. The star is torn apart, stretched into an elongated, noodle-like shape as it spirals inward before being consumed entirely by the black hole. This process, like a cosmic ballet of destruction, is both tragic and awe-inspiring. It offers a stark reminder of the sheer power of gravity, the cosmic force that shapes galaxies, stars, and everything within them. However, the occurrence of TDEs is shrouded in uncertainty. Although scientists understand the mechanics behind these events, how the immense gravitational forces of a black hole can tear apart a star, predicting when and where a TDE will occur is a different matter entirely. The stars in a galaxy follow unpredictable orbits, influenced by the chaotic gravitational interactions with nearby objects. This makes TDEs an unpredictable and fascinating mystery, one that often catches astronomers by surprise. There is also the question of how many TDEs remain undetected in our universe. Given the rarity and unpredictability of these events, astronomers have only observed a small fraction of them. The aftermath of a tidal disruption event is equally captivating. After a star is destroyed, a portion of its debris is ejected into space, forming an energetic cloud of material that radiates light across a range of wavelengths, from optical to X-rays. This luminous debris gives astronomers a valuable window into the mechanics of the event itself. But there is still much we don't understand about how this material behaves and how it converts the gravitational energy into radiation. Deciphering these processes is a crucial step in unraveling the mysteries of black holes and their role in the universe. Additionally, tidal disruption events offer an unparalleled opportunity to learn more about the environment surrounding supermassive black holes. These events reveal crucial information about the distribution of matter near the black hole and can provide insights into the growth and evolution of these cosmic giants. As we continue to observe TDEs using cutting-edge telescopes, we are likely to uncover new secrets about these enigmatic objects and deepen our understanding of the universe's most extreme phenomena. Meanwhile, closer to home, solar flares erupt with dramatic bursts of radiation from the sun's surface. These massive explosions release energy equivalent to millions of nuclear bombs going off at once. When a solar flare occurs, a wave of charged particles is launched toward Earth at incredible speeds and impacting our planet's space environment. The effect on the Earth's magnetosphere, the protective shield that guards us from solar and cosmic radiation, can be profound. Solar flares often enhance the flow of charged particles, triggering geomagnetic storms. These storms can cause magnificent auroras, lighting up the night skies with colorful displays, but they can also disrupt satellite operations, communications, and power grids on Earth. The reach of solar flares extends far beyond the atmospheric effects on Earth. For astronauts in space, solar flares are a dangerous phenomenon. They release massive amounts of radiation, which can pose serious health risks to those outside Earth's protective magnetic shield. The threat of increased radiation in space makes monitoring solar activity a critical task for space agencies to ensure the safety of astronauts. Furthermore, solar flares can interfere with high-frequency radio signals, particularly in polar regions. This can disrupt everything from aviation communications to maritime navigation, creating challenges for global communication systems. The long-term consequences of solar flares on Earth's climate and technology are equally concerning. When powerful geomagnetic storms occur, they have the potential to damage critical infrastructure, including power grids. The energetic particles can induce electrical currents that may cause transformers to fail or circuits to short, leading to widespread outages. Given the potential for disruption, scientists are intensifying their study of solar flares, hoping to better understand their patterns and predict when they might occur. Such knowledge could help mitigate the impacts of these solar events and better prepare for their far-reaching consequences. Beyond our planet, the death of stars is marked by a visually stunning event, the Planetary nebula. This beautiful, glowing shell of gas and dust forms during the late stages of a star's life, particularly in stars that are similar in size to our Sun. As a star reaches the end of its life, it can no longer sustain the nuclear fusion reactions in its core. This leads to the shedding of its outer layers, leaving behind a bright, colorful nebula. This phenomenon is not only a visually striking spectacle, but also plays a crucial role in enriching the interstellar medium, the vast, empty space between stars. The elements expelled by a planetary nebula, including carbon, nitrogen, and oxygen, are essential building blocks for future generations of stars and planets. In a sense, these nebulae serve as cosmic recycling centers, spreading the raw materials necessary for the creation of new celestial bodies. The appearance of these nebulae can vary widely, but they are often round, symmetrical, and beautifully intricate. These shapes are a result of the interaction between the expelled gases and ultraviolet radiation from the hot core of the dying star. Each planetary nebula is unique, telling the story of its progenitor star's composition and the processes that led to its eventual demise. Ultimately, the study of planetary nebulae offers crucial insights into the life cycles of stars and the processes that shape the galaxies. The materials expelled by these dying stars are recycled into the cosmic environment, where they can contribute to the formation of new stellar systems. As we continue to observe and analyze planetary nebulae, we deepen our understanding of the universe's endless cycle of birth, death, and rebirth. In the vast expanse of the cosmos, planetary nebulae hold a profound significance for astronomers, offering a unique lens into the mysterious processes of stellar evolution and the ultimate fate of stars. These nebula, often awe-inspiring in their colorful complexity, are remnants of stars that have exhausted their fuel and shed their outer layers. By closely examining the intricate characteristics of planetary nebulae, scientists can unlock crucial insights into the life cycles of stars and, more importantly, the intricate dance of their death. Through these celestial objects, we can trace the paths of stars from their birth to their inevitable demise, revealing how they evolve, transform, and contribute to the ongoing cosmic story. In studying planetary nebula, researchers not only uncover the properties of these dying stars, but also gain a deeper understanding of the forces and dynamics that govern stellar death. As we peer into the heart of these nebulae, we are, in a sense, gazing into the very soul of the universe. In this way, planetary nebulae serve as a bridge, connecting the intricate life cycles of individual stars with the broader narrative of the universe's ongoing evolution, offering a cosmic perspective that is both humbling and awe-inspiring. They remind us that, though the stars may fade, their legacy continues to shape the universe in profound ways. Moreover, cosmic strings, one of the most intriguing theoretical concepts in modern physics, open up an entirely new dimension in our understanding of space-time. These hypothetical, one-dimensional defects thought to have formed in the early universe shortly after the Big Bang are described as ultra-thin filaments of energy stretching across the cosmos. Though cosmic strings have yet to be observed directly, their potential presence offers tantalizing possibilities for unraveling the mysteries of gravitational phenomena. Imagine these strings as colossal invisible threads woven throughout the fabric of the universe, with immense masses that exert a powerful gravitational influence. The gravitational effects of cosmic strings are profound. As light passes near these theoretical strings, it bends and distorts in a manner similar to the way light is affected by the immense gravitational pull of black holes. This bending of light presents a revolutionary way of understanding gravity on the largest scales of the cosmos, offering us new insights into the structure of space itself. Could cosmic strings be the key to unlocking the secrets of gravity and space-time? The possibilities are limitless, but the intrigue doesn't end there. Cosmic strings might also provide a crucial link between two of the most fundamental pillars of modern physics, quantum mechanics and general relativity. These two theories, which govern the microscopic and macroscopic realms of the universe, respectively, have long been at odds, unable to fully reconcile with each other. The potential existence of cosmic strings could pave the way for a unified theory, bridging the gap between quantum phenomena and the gravity-driven universe of general relativity. The existence of cosmic strings might also suggest that the universe is far less homogeneous than we typically assume. Rather than a uniform, smooth expanse, the cosmos could be filled with irregularities, creating a much richer and more complex tapestry of existence. This understanding could allow physicists to explore phenomena such as gravitational waves, produced by the movements and interactions of cosmic strings. Advanced technologies may one day enable us to detect these waves, offering new glimpses into the forces that govern the universe. As we continue to probe the mysteries of the cosmos, the study of cosmic strings challenges our understanding of gravity and space-time. It pushes us to think beyond the boundaries of established theories, encouraging us to explore new possibilities and connections in our quest for knowledge. In this way, cosmic strings represent not only a speculative concept, but a powerful catalyst for deepening our understanding of the nature of reality itself. Alongside cosmic strings, another grand feature of the universe stands out: the cosmic filaments. These large-scale structures, formed by galaxies, create an intricate web that stretches across the universe. Enormous in scale, cosmic filaments can span billions of light years and are primarily composed of dark matter and gas. As the largest known structures in the cosmos, they are fundamental to understanding the distribution of galaxies and the architecture of the universe as a whole. What makes cosmic filaments particularly fascinating is their role in guiding the movement of matter across the universe. Galaxies are not scattered randomly through space. Rather, they align along these vast filaments, forming massive clusters and superclusters. This alignment is not a coincidence. It is the result of gravitational forces, where the dense regions of these filaments attract galaxies, while the less dense spaces between them form vast, empty voids. These voids, though seemingly empty, play a crucial role in balancing the structure of the universe, demonstrating the delicate interplay of attraction and repulsion on the grandest scales. The formation of these cosmic filaments can be traced back to the early universe, shortly after the Big Bang. At that time, the universe was a hot, dense place, with matter distributed relatively uniformly. However, as the universe began to cool, small fluctuations in density set the stage for gravitational instabilities. Over billions of years, these fluctuations led to the coalescence of matter into sheets and filaments, shaping the vast structures we observe today. This evolution of cosmic structures offers us a glimpse into the history of the universe and provides valuable insights into the underlying physics that govern its development. Beyond their impressive size and structure, cosmic filaments play an essential role in the ongoing formation of new stars and galaxies. As they contain vast amounts of gas, they serve as the raw material from which new stars are born. Moreover, the interaction between visible matter and dark matter along these filaments provides scientists with an unprecedented opportunity to study the elusive nature of dark matter, which constitutes a significant portion of the universe's mass, yet remains largely invisible to traditional observational methods. The study of cosmic filaments is, in many ways, a window into understanding the fundamental forces that shape the cosmos. In the grand scheme of the universe, cosmic voids occupy a fascinating position. These vast regions of space, which contain very few galaxies, stand in stark contrast to the dense clusters of stars and galaxies that populate other parts of the cosmos. Imagine a vast, empty expanse, like an enormous field surrounded by bustling cities. This is essentially what cosmic voids represent. Spanning hundreds of millions of light years, these voids are a testament to the intricacy and variety of the universe's architecture. What makes cosmic voids particularly intriguing is their relationship with dark matter. The universe is not a random scattering of matter. It follows a well-defined structure shaped by the gravitational influence of both visible and invisible components. Dark matter, which makes up a substantial portion of the universe's total mass, does not emit light or energy, making it nearly impossible to detect directly. Yet, its gravitational pull profoundly influences the distribution of galaxies and galaxy clusters. Voids represent areas where dark matter's gravitational influence is weaker, resulting in fewer galaxies and a more sparsely populated region of space. These empty expanses offer a unique opportunity to study the nature of dark matter, as well as the overall evolution of the universe. By mapping the boundaries of cosmic voids, scientists can glean valuable information about the distribution of dark matter, offering new insights into the forces that govern cosmic structure. In essence, voids highlight the ways in which dark matter clumps together in some areas, leaving vast, empty regions in its wake. The study of cosmic voids is an essential part of understanding the universe's grand design. By exploring these enigmatic regions, scientists hope to unlock the secrets of the universe's structure, revealing the intricate gravitational web woven by dark matter and its profound influence on the formation and evolution of galaxies. As the universe expanded, regions that once contained galaxies evolved into vast voids, offering new perspectives on the early universe and the dynamic forces driving cosmic expansion. These voids, seemingly empty spaces between the grand clusters of galaxies, could hold crucial clues about how the cosmos evolved. Once rich in galaxies, these areas may have transformed as structures elsewhere grew, shaped by the invisible yet powerful force of dark matter. This ongoing exploration of voids doesn't merely enrich our understanding of cosmic evolution, but also challenges existing theories about the universe's formation. By studying these vast expanses of emptiness, scientists are gaining a clearer picture of the delicate interplay between visible matter, dark matter, and the fabric of the cosmos itself. At the other end of the cosmic spectrum, galaxy clusters stand as some of the most monumental structures in the universe. These clusters, which consist of hundreds to thousands of galaxies bound together by gravity, serve as both a historical record and a lens through which we can study the evolution of the cosmos. In addition to their galaxies, these clusters also contain vast amounts of hot gas and dark matter, making them essential for scientists seeking to understand the universe's intricate design. Through these stellar gatherings, we gain invaluable insights into how the universe has transformed over billions of years. Galaxy clusters are not just large-scale formations, but also the culminating structures in the universe's ongoing process of growth. After the Big Bang, as the universe expanded and cooled, slight variations in matter density created gravitational instabilities. These fluctuations set the stage for larger structures to take shape. Over time, these instabilities attracted matter, both visible and invisible, causing clusters to form as gravity drew dark matter and regular matter together. This process of structure formation is pivotal to our understanding of cosmic evolution, marking the shift from small, thus dense regions of matter to the vast galaxy clusters we observe today. The study of galaxy clusters offers a remarkable window into the timeline of cosmic events. One of the most vital tools in this investigation is the analysis of redshift, the phenomenon where the light from distant galaxies shifts toward longer wavelengths as the universe expands. By measuring the redshift in the light emitted by galaxies within a cluster, scientists can determine their distances and velocities. This reveals how clusters have moved and interacted over time, shedding light on the ever-expanding nature of the universe. Furthermore, the study of the intracluster medium, the hot gas found within galaxy clusters, offers yet another layer of insight into the universe's history. This gas, which emits X-rays, serves as a thermometer, revealing the temperature and density of the environment within these clusters. By studying the interplay of gravity and temperature over time, scientists can gain a deeper understanding of how these immense structures formed and evolved. Each galaxy cluster, with its unique composition and history, tells a story that contributes to the broader narrative of the universe's evolution. Through these clusters, we not only learn about the origins of the cosmos, but also our place within this vast and ever-expanding universe. In the pursuit of understanding cosmic dynamics, the discovery of the Great Attractor has added another fascinating chapter to our exploration of the universe's structure. This vast gravitational anomaly, discovered in the late 20th century, lies about 200 to 250 million light-years from Earth in the direction of the Centaurus constellation. The Great Attractor represents a massive gravitational focal point, pulling galaxies, including our own Milky Way, toward it. The discovery of this immense gravitational pull has profoundly changed how we perceive the movement of galaxies, illustrating that galaxies are not isolated, drifting freely, but are instead drawn toward a singular cosmic force. The Great Attractor has revealed that entire galaxy clusters and even superclusters are being affected by this gravitational anomaly. It acts almost like a cosmic traffic jam, where galaxies appear to be trapped in a vast gravitational embrace. This region of space is an essential feature in understanding the large-scale structure of the universe. It helps scientists piece together the intricate distribution of matter across vast distances and offers a clearer picture of the forces governing the universe on the grandest scales. What makes the Great Attractor even more intriguing is its location within the local supercluster, a vast collection of galaxies that includes the Milky Way. This insight is crucial because understanding the behavior of gravitational forces within our local supercluster provides valuable information about the larger universe. The Great Attractor's gravitational pull not only influences the motion of entire galaxy clusters, but also supports the idea that gravity is a universal force that governs both stars within galaxies and galaxies within the cosmos. Beyond visible matter, the Great Attractor also holds key information about dark matter, an elusive substance that remains largely invisible but is thought to make up a significant portion of the universe's mass. As galaxies move toward the Great Attractor, they reveal not only the visible matter in the form of stars and gas, but also the unseen dark matter that contributes to the gravitational pull. This ongoing study of the Great Attractor is helping scientists uncover the hidden forces shaping the universe, adding another layer to our understanding of cosmic formation and evolution. Connected to the Great Attractor and other similar gravitational anomalies is the cosmic web, a vast and intricate structure that maps the distribution of matter in the universe. This cosmic web consists of interconnected filaments of dark matter and galaxies outlining the largest structures in the universe. The web forms a network of nodes where galaxies cluster and vast voids or empty spaces that separate these concentrations. This cosmic framework offers a deeper understanding of how the universe has evolved since the Big Bang. One of the most remarkable aspects of the cosmic web is the role of dark matter. Although invisible, dark matter's presence is felt throughout the universe as it shapes the formation of galaxies and large-scale structures. During the universe's expansion, regions with higher concentrations of dark matter began to exert gravitational forces, pulling in ordinary matter and forming the first galaxies. This process is fundamental to understanding how galaxies group together in clusters and how vast voids came to exist between them. The cosmic web structure, shaped by dark matter, reveals not only the universe's past, but also provides clues about the forces still at work, guiding the evolution of the cosmos on a grand scale. As we look deeper into the cosmic web, we find ourselves piecing together a grand puzzle. Through the study of galaxy clusters, voids, and gravitational anomalies like the Great Attractor, we are uncovering the hidden forces and intricate structures that have shaped our universe. The story of the cosmos is one of continuous evolution, driven by gravity, dark matter, and the forces that bind all matter together. With each discovery, we gain a clearer view of the vast, interconnected universe that we are part of, revealing how each galaxy, star, and planet fits into this grand cosmic narrative. The cosmic web, a vast and intricate structure of galaxies, filaments, and voids, offers us a unique lens through which to understand the evolution and fate of the universe. At the heart of this web lies a critical phenomenon known as cosmic inflation, an extraordinary period of rapid expansion that took place just moments after the Big Bang. This inflationary period stretched space at an unimaginable rate, smoothing out the initial irregularities in the universe and imprinting it with tiny fluctuations. These fluctuations, which were minuscule at the time, would gradually grow into the complex cosmic structures we observe today. As we study the cosmic web, we gain a deeper understanding of these ancient processes, helping us to decode the events that led to the current arrangement of galaxies. Consequently, the study of the cosmic web isn't merely about understanding where galaxies are located today. It provides us with a window into the history of our universe, from its violent beginnings to its potential futures. These observations give rise to profound questions about the forces that govern the cosmos. For instance, mysterious phenomena such as the alignment of galaxy clusters and the enigmatic behavior of dark energy continue to puzzle scientists, leading to new theories and explorations. Each new discovery not only fills in pieces of the cosmic puzzle, but also opens up new questions, illustrating that the cosmic web is as much a map of the past as it is a guide to the future. It serves as both a record and a roadmap for the universe yet to unfold. One of the most intriguing aspects of our cosmic neighborhood is the behavior of the satellite galaxies that orbit the Milky Way. These galaxies, although smaller and less luminous than their larger counterparts, provide valuable clues about the elusive nature of dark matter, a substance that doesn't emit, absorb, or reflect light and remains invisible to our telescopes. Instead, dark matter is detectable only through its gravitational effects. When astronomers observed the 9 main satellite galaxies orbiting the Milky Way, they noticed a curious pattern. Rather than being scattered randomly throughout space, these galaxies appear to follow a specific orderly arrangement. This clustering challenges traditional models of galaxy formation, prompting astronomers to propose that the galaxies are being influenced by an invisible, massive entity, the very dark matter we seek to understand. This hypothesis is bolstered by the gravitational pull that dark matter exerts on these satellite galaxies. Models that incorporate dark matter can replicate the observed distribution and velocities of the satellites, suggesting that dark matter is not just a theoretical construct, but a substantial and active component of the universe, shaping the behavior of galaxies. Moreover, the alignment of these satellite galaxies, which tend to lie in a thin, flattened disk, adds further weight to this theory. If their formation were the result of random processes, such a configuration would be highly improbable. Instead, scientists now propose that the distribution of dark matter around the Milky Way mirrors this disk-like arrangement, hinting at an extended dark matter structure that is central to understanding cosmic formation and evolution. In exploring the dynamics of these satellite galaxies, researchers can unlock secrets about dark matter itself. The study of how these galaxies move and interact with invisible forces around them offers a rare opportunity to observe dark matter's properties in action. As we continue to study these cosmic structures, we move closer to unraveling one of the most enduring mysteries in modern astrophysics. In the broader scope of cosmic evolution, galactic mergers play a pivotal role in shaping the structures we observe in the universe today. These cosmic collisions occur when two or more galaxies are drawn together by their mutual gravitational attraction, eventually merging into a single, larger galaxy. The effects of these mergers are far-reaching, influencing everything from the size and shape of the galaxies to the rate at which new stars are born within them. The aftermath of a galactic merger can be spectacular, bursting with intense star formation, the disruption of existing stellar systems, and the release of enormous amounts of energy. These cosmic events dramatically alter the galactic landscape, creating new structures and laying the groundwork for the formation of supermassive black holes, which play critical roles in the evolution of galaxies. Galactic mergers help us understand the history and growth of galaxies. For example, the Milky Way itself is believed to have grown in size and complexity partly through the absorption of smaller galaxies in the distant past. These interactions not only increase a galaxy's size, but also contribute to the development of the supermassive black hole at its center, which can influence the entire galactic ecosystem. On a larger scale, galactic mergers affect the distribution of galaxies and may shape the formation of galaxy clusters, providing astronomers with clues about the past and future of the cosmos. As we delve into the mysteries of cosmic evolution, we also encounter one of the most fascinating and energetic phenomena in the universe: cosmic rays. These high-energy particles, primarily protons, but also including heavier nuclei and electrons, travel across vast distances at speeds approaching the speed of light. When these cosmic rays collide with atoms in Earth's atmosphere, they produce secondary particles that can be detected here on the ground, allowing scientists to study them. The energy of cosmic rays is so immense that their study offers a window into some of the most powerful processes occurring in the universe. Cosmic rays often originate from extreme events such as supernovae, active galactic nuclei, and neutron stars, where vast amounts of energy are released, accelerating particles to nearly unimaginable speeds. In examining cosmic rays, researchers can uncover the dynamics of these high-energy processes, helping to understand the mechanisms behind some of the most energetic phenomena in the cosmos. Interestingly, these particles also challenge our current understanding of particle physics. The highest energy cosmic rays, which carry more energy than anything achievable with human-made particle accelerators, defy explanation. Scientists are working hard to uncover the sources and acceleration processes behind these particles, testing the limits of our knowledge of physics. In this way, cosmic rays serve as messengers from the farthest reaches of the universe, providing us with valuable information about the most extreme conditions in space and allowing us to test our theories of the universe's most fundamental forces. Alongside the study of cosmic rays, one of the most exciting areas of research in astrophysics revolves around weakly interacting massive particles, 1MePs, one of the leading candidates in the search for dark matter. Dark matter is a mysterious and invisible substance that exerts a gravitational pull on visible matter, but cannot be detected directly by conventional means. WIMPs are theoretical particles that interact with ordinary matter via the weak nuclear force, making their interactions rare and difficult to detect. The idea behind WIMPs is that in the early universe, these particles were produced in abundance, and as the universe expanded and cooled, they froze out and became a dominant component of dark matter. Despite their elusive nature, WIMPs could account for a significant portion of the universe's mass and help explain the gravitational forces that hold galaxies and galaxy clusters together. To detect WIMPs, researchers use highly sensitive detectors placed deep underground, where cosmic radiation is minimal, in the hopes of observing a rare interaction between WIMPs and normal matter. These interactions are incredibly rare, occurring only once in billions of years, making the detection of WIMPs a formidable challenge. Yet, as technology advances and new detection methods are developed, scientists continue to search for these particles, hopeful that uncovering their existence will lead to a greater understanding of dark matter and its role in the cosmos. The search for weakly interacting massive particles, WIMPs, peeps, is an adventure into the unexplored frontiers of physics, one that promises to unlock the deepest mysteries of the universe. These elusive particles, if discovered, could hold the key to understanding some of the most profound cosmic phenomena, most notably dark matter. Dark matter, which makes up a significant portion of the universe's mass, remains invisible and undetectable by conventional means. But WIMPs could offer us a direct link to this hidden component of the cosmos. The hunt for WIMPs is not merely an academic pursuit. It is a mission to reveal the very fabric of reality itself. The potential confirmation of WIMPs would not only explain the dark matter conundrum, but would also bridge the vast, often complex gap between the realms of particle physics and cosmology. As researchers continue to develop ever more sophisticated methods of detecting these particles, the boundaries of our scientific knowledge are being expanded. With each new experiment, we take another step toward understanding the true composition of the universe and its fundamental workings. In parallel, the evolution of solar systems tells a breathtaking tale of creation, governed by an intricate interplay of physical forces. At their birth, solar systems emerge from vast molecular clouds, massive cold clouds of gas and dust scattered across space. These clouds collapse under their own gravity, and over time, this collapse leads to the formation of a central star. The remaining material surrounding this new star begins to clump together, gradually forming the planets, moons, asteroids, and comets that we observe in the solar system today. This process unfolds over millions of years, with each solar system developing its own unique combination of celestial bodies. A critical factor in the diversity of solar systems lies in the composition of the molecular cloud from which they form. The types and proportions of elements present, ranging from the lightest gases like hydrogen and helium to heavier elements such as carbon and nitrogen, dictate the types of planets that emerge. For example, a cloud rich in heavier elements may give rise to rocky planets like Earth and Mars, while one abundant in lighter elements might favor the formation of gas giants like Jupiter and Saturn. Moreover, the early conditions of the solar system, temperature gradients, the proximity of neighboring stars, and the interactions within the cloud further shape the evolution of planets. Gravitational forces also play a vital role. As planets form, their orbits can be influenced by the gravitational pull of nearby objects, including their parent star and even other stars in the neighborhood. Over time, these forces can dramatically alter the configuration of the solar system. Planets may be ejected from their original orbits, asteroid belts may form, or even entire planets may merge. These gravitational interactions can lead to a wide variety of solar system structures, from tightly packed systems to those with vast distances between planets. Furthermore, external events like supernova explosions or the passing of nearby stars can inject additional complexity into a solar system's evolution, triggering shockwaves that either catalyze new formation processes or disrupt existing ones. Such dynamics, both internal and external, highlight why solar systems are so varied. Studying these processes helps us understand the remarkable variety of solar systems in the universe, including our own. It gives us a deeper appreciation for how our solar system came to be and how it fits into the broader cosmic landscape. Tidal forces, one of the most fascinating phenomena in astronomy, are a direct consequence of the gravitational interactions between celestial bodies. These forces arise when one object in space exerts a gravitational pull on another, causing distortions in shape. A familiar example of this effect is the moon's gravitational pull on Earth's oceans, creating the tides. But tidal forces extend beyond oceans. They influence the entire structure and internal dynamics of planets and moons. When two celestial bodies are close enough, the gravitational interaction between them can cause each body to deform, leading to what is known as a tidal bulge. The side facing the other object experiences a stronger gravitational pull, while the far side experiences a weaker pull, resulting in stretching and squeezing. In some cases, this tidal interaction is so intense that it leads to significant geological activity. For example, Jupiter's powerful gravitational pull causes the volcanic eruptions on its moon Io, making it one of the most geologically active bodies in the solar system. These forces also affect the orbital dynamics of celestial bodies, influencing their movement over time. One striking example is the gradual movement of the moon away from Earth at a rate of about 4 centimeters per year. This slow drift is a result of the transfer of Earth's rotational energy to the moon due to tidal interactions. Studying these tidal forces provides valuable insight into not only individual celestial bodies, but also the broader systems they are part of. By examining the impact of tidal forces on planets and moons, scientists can reconstruct their evolutionary histories, understand their present-day behaviors, and predict future changes. Tidal forces offer a powerful lens through which we can view the interconnectedness of celestial bodies across the universe, illustrating how each object influences the others in a complex cosmic dance. One of the most important tools for understanding the universe's expansion is redshift, a phenomenon that describes how light from distant objects shifts toward the red end of the spectrum as they move away from us. The mechanism behind redshift is rooted in the laws of physics. When an object emitting light moves away, the wavelengths of that light stretch, causing it to appear redder. This principle, first demonstrated by astronomer Edwin Hubble in the early 20th century, became the cornerstone of modern cosmology. Hubble's observations revealed that most galaxies are moving away from the Milky Way, and the farther away a galaxy is, the faster it appears to recede. This relationship, now known as Hubble's law, provided the first evidence that the universe is expanding. Redshift plays a crucial role in our understanding of the universe's structure and evolution. By measuring the degree of redshift in the light from distant galaxies, scientists can determine their distance from Earth, helping to map the vast expanse of the universe. This measurement also helps scientists calculate the rate of expansion, leading to discoveries about dark energy, a mysterious force believed to be accelerating this expansion. Redshift, therefore, is more than just a curious observational phenomenon. It is a powerful tool that opens the door to understanding the universe's origins, its ongoing evolution, and its ultimate fate. Each galaxy's light, altered by time and space, holds a story about the universe, a story that stretches back billions of years and continues to unfold before us. Finally, the discovery of supermassive black holes at the centers of galaxies has revolutionized our understanding of these enigmatic cosmic entities. These black holes, often millions or even billions of times the mass of the Sun, lie at the heart of most galaxies, including our own Milky Way. Observing these colossal structures provides scientists with invaluable insights into their formation, evolution, and role in the cosmic ecosystem. One of the most fascinating aspects of supermassive black holes is their influence on galaxy formation. As these black holes grow, they exert a powerful gravitational pull on the gas and stars in their vicinity. This pull can trigger the formation of new stars, or conversely, suppress star formation, a phenomenon known as feedback. Understanding how black holes interact with their surroundings allows astronomers to decipher the complex process of galaxy evolution. This relationship between black holes and galaxies is crucial to understanding how galaxies develop over time and how they become the magnificent structures that we see in the universe today. The discovery and study of black holes are not just about these mysterious objects themselves, but about the broader cosmic processes they are part of, processes that shape the very fabric of our universe. Each new discovery about black holes brings us closer to understanding the fundamental workings of the cosmos. Furthermore, the study of black holes plays a crucial role in expanding our understanding of the most fundamental aspects of physics, including the nature of gravity and how matter behaves under extreme conditions. At the heart of these enigmatic objects lies the event horizon, the so-called point of no return, where the gravitational pull is so intense that nothing, not even light, can escape its grasp. This boundary pushes our current understanding of the laws of physics to their very limits, often leading to compelling debates between the theories of quantum mechanics and general relativity. Observing these cosmic giants, however, may soon provide us with answers to some of the most profound questions about the universe. One of the greatest challenges in modern theoretical physics lies in understanding what happens at the intersection of these two dominant theories. As scientists probe deeper into the behaviors of black holes, particularly in the context of their event horizons, they may be able to uncover groundbreaking insights into the fabric of space-time itself. These observations could reveal new principles of physics that merge quantum mechanics with Einstein's theory of gravity. The sheer presence of a supermassive black hole, typically located at the heart of most galaxies, also acts as a cosmic clock, offering valuable insights into the history and age of the galaxy it resides in. By studying the motion of stars and gas in the central regions of these galaxies, astronomers can estimate the black hole's influence over time. This not only allows them to piece together the history of the galaxy itself, but it also provides a broader picture of how galaxies evolve. These supermassive black holes act as markers for understanding galactic formation and development across the entire cosmos. The implications of studying black holes extend far beyond just the black holes themselves. These objects offer a gateway to explore many more profound questions about the universe, such as how galaxies form, how they evolve, and how the dark matter that pervades the cosmos shapes the structures we observe. Their role as laboratories for understanding the most extreme environments in the universe cannot be overstated, making them indispensable to our ongoing exploration of the cosmos. Star clusters, another fascinating cosmic formation, emerge from the gravitational collapse of dense regions of gas and dust in space. These molecular clouds, rich in raw materials, fragment and collapse under their own weight, ultimately giving birth to new stars. When a group of stars forms in close proximity to one another, they become a star cluster, a tightly bound group that can vary greatly in size and age. There are two primary types of star clusters: open clusters and globular clusters. Open clusters are younger and typically looser collections of stars, whereas globular clusters are much older and have stars that are more tightly bound together by gravity. The study of these clusters offers astronomers a rare opportunity to investigate stellar dynamics, the interactions and behaviors of stars within a gravitational field. By examining the ways in which stars in a cluster influence one another, scientists can learn a great deal about how stars evolve over time, particularly in environments where their gravitational interactions shape their behavior. As stars in a cluster age, they gradually evolve, with their positions and velocities changing over time. This provides astronomers with a rich tapestry of data that allows them to understand the life cycles of stars, including how they are formed, how they change over billions of years, and even how they die. Through the observation of these processes, astronomers can build more accurate models of stellar evolution. Moreover, studying star clusters can shed light on the distribution of mass across the universe. For instance, globular clusters, which contain a vast number of stars bound tightly together by gravity, offer an excellent way to study the motion of these stars in order to calculate the total mass of the cluster. This information, in turn, can be used to make inferences about the presence of dark matter surrounding these clusters, matter that does not emit light, but whose gravitational effects can be observed. Star clusters, therefore, act as powerful cosmic laboratories, not just for understanding the stars themselves, but for unlocking the mysteries of the larger structures that form the framework of our universe. These clusters are much more than just beautiful arrangements of stars. They are pivotal to understanding how stars interact, how they evolve over time, and how they contribute to the larger fabric of the universe. Each cluster holds valuable clues to the origins and development of stars, making them an indispensable tool in our quest to understand the astronomical realm. As we delve deeper into the study of these clusters, we unlock more of the cosmic mysteries surrounding the birth and evolution of stars, enriching our understanding of the universe itself. When astronomers investigate the rotation curves of galaxies, they are essentially measuring how fast stars and gas orbit around the center of the galaxy in relation to their distance from the galactic core. Based on the amount of visible matter, predictions suggest that the speed of objects should decrease as they move further away from the center. However, astronomers have noticed a fascinating anomaly. In many spiral galaxies, rotation curves remain flat, or even increase in speed, as the distance from the center grows, instead of declining as would be expected. This unexpected behavior points to a deeper mystery, the gravitational pull of unseen matter that is maintaining the high speeds of stars and gas in the outer regions of these galaxies. This unseen material, which does not emit light, is what we refer to as dark matter. The discovery of these anomalous rotation curves has been one of the key pieces of evidence supporting the existence of dark matter, a form of matter that makes up a significant portion of the universe, but is undetectable by traditional telescopes. Another intriguing observation involves the motion of satellite galaxies, which orbit around larger galaxies. Instead of moving according to the visible matter distribution within the larger galaxy, many of these smaller galaxies display motion patterns that suggest they are all moving in synchrony. This alignment is unexpected given their distances from one another and hints at the profound influence of dark matter, which seems to be holding these satellite galaxies in place, preventing them from drifting away from their larger counterparts. These mysterious measurements have sparked significant discussions among astrophysicists. It's raising questions not only about our understanding of gravity, but also about the formation and behavior of galaxies, and even the larger scale structure of the universe. The implications of these findings stretch beyond individual galaxies, challenging scientists to rethink how dark matter affects the universe on a grand scale. Helical galaxies present yet another fascinating twist in our understanding of galaxy formation, offering new challenges to traditional models of spiral galaxies. Traditionally, spiral galaxies have been envisioned as flat, rotating disks with stars and gas organized into prominent arms. These arms are thought to form through density waves, regions where mass concentrations generate gravitational effects that pull in more material, creating the characteristic spiral shapes we associate with these galaxies. However, helical galaxies challenge this conventional view, offering an intriguing alternative to how galaxies can form and evolve. In these galaxies, the structure is far more complex, adding to the richness of our understanding of how galaxies can take shape and evolve over cosmic time. Studying these galaxies provides us with invaluable clues, not just about their individual histories, but also about the broader processes of galactic formation and evolution throughout the universe. By delving into the study of such galaxies, we continue to expand our understanding of the dynamic forces that shape the cosmos. However, helical galaxies deviate substantially from the well-established models of galaxy formation, presenting a phenomenon that has intrigued astronomers for decades. Unlike the traditional flat disk-shaped galaxies we often observe, these helical galaxies exhibit a dynamic and three-dimensional structure that is more complex and visually striking. Instead of maintaining a steady, stable form, these galaxies twist and spiral in a corkscrew-like motion, adding a layer of complexity to our understanding of galactic dynamics. As one gazes into the heart of these galaxies, the sight is mesmerizing, a swirling dance of stars, gas clouds, and cosmic dust, spiraling upward in an almost organic flow. The patterns they create are anything but static. They are a breathtaking, ever-shifting display of cosmic forces at work. This peculiar, twisted shape of helical galaxies raises several fundamental questions regarding the mechanisms responsible for their formation and evolution. What causes these galaxies to deviate so drastically from the conventional flat structures observed in the majority of galaxies? Could there be processes at play that are not yet fully understood, processes that might alter how we view the evolution of galaxies on a larger scale? One of the most significant challenges posed by these galaxies is the potential inadequacy of current models that attempt to explain the formation of galaxies. Traditional theories often emphasize gravity's role in pulling matter together over vast periods of time, but the twisted, corkscrew structure of helical galaxies implies that other forces or factors might be influencing their development in ways we have yet to fully explore. For instance, the formation of such intricate helical shapes might point to the influence of external gravitational forces, such as the pull of neighboring galaxies or the turbulence within a galaxy itself, playing a more crucial role than initially thought. It's possible that the angular momentum of the galaxy, combined with interactions between neighboring cosmic bodies, could contribute to the twisting motion that results in these helical formations. This suggests that galaxy formation is not a simple matter of gravitational attraction alone, but may involve more complex interactions between galaxies and their environment. The existence of helical galaxies, therefore, compels astronomers to reevaluate the models and theories that have shaped our understanding of galactic evolution. It emphasizes the profound diversity of galactic structures and highlights the intricate forces at play in the vast expanse of the cosmos. As we continue to study these captivating celestial phenomena, we are bound to uncover more secrets about the mechanisms driving the formation of galaxies, offering us a deeper appreciation for the beauty, complexity, and dynamic nature of the universe. In a different realm of cosmic wonders, planetary nebulae stand as some of the most visually stunning and scientifically perplexing objects in the universe. These nebulae form when stars of medium size, similar to our Sun, reach the end of their life cycle. As these stars exhaust their nuclear fuel, they expel their outer layers into space, creating intricate and colorful shells of gas and dust that glow with vibrant hues. While the basic process is well understood, the diversity and complexity found within planetary nebulae present astronomers with new challenges and questions about stellar evolution. Among the most intriguing aspects of planetary nebulae is their diverse range of shapes. Traditionally, nebulae have been thought to exhibit fairly simple, round, or elliptical configurations. Yet, many planetary nebulae defy this norm, showcasing intricate, hourglass-like shapes or bipolar structures that seem to challenge the conventional models. These unusual forms suggest that the formation of planetary nebulae may be influenced by a variety of factors not yet fully understood, such as the pressure exerted by surrounding stellar winds or interactions with companion stars. Some nebulae might even contain the remnants of earlier stellar mass ejections, which contribute to the chaotic yet strikingly beautiful patterns observed in these objects. In addition to their remarkable shapes, the chemical composition of planetary nebulae adds another layer of complexity to their study. While hydrogen and helium are the most common elements found in nebulae, some have revealed the presence of heavier elements, such as carbon, oxygen, and even nitrogen, elements typically formed through rare processes in the cores of stars. This chemical diversity suggests that the process of stellar nucleosynthesis, where elements fuse in the cores of stars, plays a crucial role in enriching the interstellar medium. When stars expel their outer layers at the end of their lives, they are essentially seeding the cosmos with heavier elements, which in turn influences the formation of new stars and planets. These unexpected features of planetary nebulae not only captivate astronomers, but also challenge our existing model stellar life cycles. As we continue to explore these phenomena, we are reminded of the unpredictable nature of the universe and the dynamic processes that shape it. With advancements in observational technologies, astronomers are likely to uncover even more surprises hidden within the colorful clouds of planetary nebulae, deepening our understanding of the universe's complexities and offering a glimpse into the fascinating life cycles of stars. Equally captivating is the cold spot in the cosmic microwave background, CMB, an anomaly that has baffled scientists and ignited debates about the universe's origins. The CMB is the faint afterglow of the Big Bang, providing a snapshot of the universe just 380,000 years after its birth. It offers a unique look into the infant universe, revealing the faint echoes of cosmic events that occurred at a time when the universe was still in its infancy. The cold spot in the CMB is an intriguing feature, a region that appears cooler than its surrounding areas. It stretches across a significant portion of the sky and has raised many questions about its origin. One of the leading theories suggests that this cold spot may be the result of a super void, an enormous region of space with fewer galaxies than average. As the cosmic microwave background radiation passes through such an area, it could be stretched and cooled, creating the observed temperature anomaly. Another theory posits that the cold spot may be the result of cosmic fluctuations, variations in the density of matter in the early universe, that were amplified over time, leaving behind regions with different temperatures in the CMB. The cold spot in the CMB is an extraordinary mystery that continues to spur research and debates among scientists. Understanding its origins and implications could provide valuable insights into the early universe and the processes that led to the formation of the cosmic structures we see today. As researchers continue to study this enigmatic region, they may uncover new secrets about the universe's birth, evolution, and expansion, adding another layer to our ever-growing understanding of the cosmos. Lastly, the formation of moons around gas giants such as Jupiter and Saturn represents another fascinating aspect of planetary science. These massive planets possess numerous moons, each with its own unique characteristics and history. Some moons are thought to have formed simultaneously with their parent planets, created from the leftover gas and dust in the early solar system. Others, however, may have originated from entirely different regions, captured by the gravitational pull of the gas giants as they pass through the solar system. This diversity of moon types, ranging from small, irregularly shaped bodies to large, spherical moons, offers valuable clues about the dynamics of planetary formation and the forces that govern the evolution of moons and planets alike. The study of moons around gas giants reveals much about the processes that govern the formation of our solar system. These moons can offer insights into the conditions that prevailed in the early solar system, shedding light on the interactions between planets and their moons, and revealing the complex forces that shape the system we inhabit today. As our exploration of these moons continues, we may uncover even more surprising and fascinating details about the birth and evolution of our solar system. Moons, in all their incredible variety, have origins that are as diverse as the planets they orbit. Some moons, for example, were not born around their host planets, but were instead captured from the far reaches of space, perhaps even from the outer solar system. These captured moons, in particular, present a fascinating puzzle for astronomers and planetary scientists. Take, for instance, the irregularly shaped moons of Jupiter, such as Himalaya. These bodies likely began their journey far beyond Jupiter in the distant Kuiper Belt, before being snatched by the giant planet's immense gravitational pull. This process of capture results in moons of varying sizes and shapes, each following eccentric orbits that often tilt at odd angles compared to their planet's equator. Some of these moons' orbits are so eccentric that they seem almost chaotic. As these moons are drawn into their orbits, they often begin to exhibit another intriguing phenomenon: tidal heating. The immense gravitational forces exerted by gas giants like Jupiter create intense friction within the moon's interior. This friction generates heat, which can sometimes lead to volcanic activity or geological upheaval. One of the best examples of this phenomenon is Io, one of Jupiter's largest moons. Io is not just a moon, it's the most volcanically active body in the entire solar system. The volcanic eruptions that spew across Io's surface are a direct result of tidal heating, as Jupiter's gravity constantly flexes the moon's interior. As a result, the surface of Io is continuously reshaped, making it a dynamic and evolving world. These moons, far from being static, are constantly changing, driven by both the gravitational interactions they experience and the internal heat generated within them. In fact, the interactions between moons can sometimes lead to even more complex scenarios. Many moons, especially those in close proximity to one another, exert gravitational forces that influence each other's orbits or even trigger geological activity. This interconnectedness creates a dynamic system where the movements and behaviors of one moon can cause ripples across the entire satellite system. It's a testament to how the solar system is a living, breathing place, where even the most distant moons are part of a larger, constantly evolving cosmic dance. The formation and behavior of moons around gas giants is not only a remarkable chapter in the history of our solar system, but also a fascinating study of gravitational mechanics, tidal forces, and cosmic evolution. These moons, with their strange orbits, eccentric shapes, and active geological features, continue to captivate astronomers and stoke the imagination of anyone who looks up at the night sky. Meanwhile, another spectacular cosmic phenomenon, the Fermi bubbles, stretches our understanding of the universe in entirely different ways. These massive structures, which were discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope, exist in the very heart of our galaxy, the Milky Way. The Fermi bubbles are vast regions of gamma-ray emissions extending about 25,000 light-years above and below the galactic plane. What makes these bubbles so intriguing is not only their immense size, but also the intense energy they reveal. Their presence challenges astronomers to reconsider our understanding of the processes that govern the dynamics of our galaxy. The leading theory surrounding the origin of the Fermi bubbles points to the supermassive black hole at the center of the Milky Way, known as Sagittarius A star. Around 2 million years ago, this black hole is thought to have experienced a period of rapid accretion in which it consumed an extraordinary amount of material from its surroundings. The violent release of energy during this event could have generated powerful jets of particles and radiation, which then burst outward from the galactic center in explosive outbursts. These energetic jets would have created the bubble-like structure that we now observe. However, an alternative theory suggests that the Fermi bubbles could have been created by intense star formation in the galactic core. The center of the Milky Way is a region rich in massive stars, many of which end their lives in supernova explosions. These catastrophic events send shockwaves through space, pushing gas and dust outward, potentially forming the characteristic bubbles we observe today. A sequence of supernovae over millions of years could have cumulatively created the structures seen in the Fermi bubbles. The importance of the Fermi bubbles goes beyond just their size. They serve as cosmic beacons, providing us with valuable insights into the energetic processes occurring at the heart of our galaxy. They are a reminder of how much we still have to learn about galactic evolution and the fundamental forces that shape the universe. As scientists continue to investigate these bubbles, they open a window into the most energetic and mysterious regions of space, offering a deeper understanding of the Milky Way's past, present, and future. In the early 20th century, Edwin Hubble made revolutionary discoveries that reshaped our understanding of the universe. One of his most profound contributions was the identification of what he called galaxy walls, vast, interconnected structures composed of clusters and filaments of galaxies. These cosmic walls reveal the large-scale structure of the universe, showing that galaxies are not randomly scattered, but are instead organized in interconnected patterns, creating a network known as the cosmic web. Before Hubble's work, the prevailing view was that galaxies were spread evenly across the universe. But Hubble's observations uncovered something far more intricate: enormous voids and dense regions filled with galaxy clusters. These galaxy walls, made of vast sheets and filaments of galaxies, are the very fabric of the cosmos. By mapping these structures, astronomers can study how gravity has shaped the universe's large-scale structure, influencing the distribution and movement of galaxies across vast cosmic distances. Understanding these galaxy walls is also crucial for unlocking the history of the universe itself. The patterns of these structures give us clues about the early universe, immediately following the Big Bang. In those first moments of cosmic expansion, density fluctuations in the primordial gas eventually led to the formation of galaxies and clusters of galaxies. The study of galaxy walls also has profound implications for our understanding of dark matter and dark energy, the mysterious forces that are believed to play a significant role in shaping the structure of the universe. Hubble's pioneering work set the stage for modern studies of the cosmos, and today, with advanced telescopes and increasingly sophisticated techniques, scientists continue to explore these massive cosmic structures in greater detail. The study of galaxy walls not only provides insight into the architecture of the universe, but also raises important questions about its fate. As we look deeper into these vast formations, we begin to realize just how interconnected everything in the universe truly is. A cosmic web of galaxies, stars, and dark matter, all working together to create the ever-expanding universe we observe today. Neutrinos, often called ghost particles, are some of the most mysterious and elusive entities in the universe. These tiny, nearly massless particles are incredibly abundant, with billions of them passing through our bodies every second without leaving a trace. Despite their near invisibility, neutrinos are crucial for our understanding of fundamental processes in the universe. Their unique properties make them invaluable for studying some of the universe's most energetic events, such as nuclear fusion in stars, supernova explosions, and even the conditions just moments after the Big Bang. The importance of neutrinos lies in the fact that they carry information about the environments they come from. When a supernova occurs, for example, neutrinos can escape from the dense core of the dying star long before any light can. By detecting these neutrinos, scientists gain insight into the processes that take place within a star's core, information that would otherwise be hidden from us. In a sense, neutrinos act as messengers, bringing us data from some of the most extreme and enigmatic events in the universe. As scientists continue to study neutrinos, they hope to unlock new mysteries about the birth and evolution of stars, the formation of galaxies, and even the very nature of the universe itself. These ghostly particles, though nearly invisible, hold the key to understanding some of the universe's most fundamental processes, offering us a unique glimpse into the heart of cosmic phenomena. Studying neutrinos presents a unique and challenging endeavor for physicists, largely because of their elusive nature. These tiny, nearly massless particles can pass through ordinary matter as though it isn't even there, with almost no interaction. Their ability to slip past detectors with ease has posed a significant obstacle in understanding their properties. As a result, scientists have had to come up with creative ways to capture these ghostly particles. To detect them, they often need to use massive detectors, sometimes located deep underground or beneath the ocean. These locations help minimize interference from other particles, which might otherwise drown out the signal. The detectors themselves are often vast pools of water or ice, designed to catch the rare collision of a neutrino with another particle. When a neutrino interacts with these substances, it may produce a faint flash of light, a faint yet critical clue that researchers can measure. Although the process of observing neutrinos is complex and fraught with difficulty, technological advancements are steadily improving our ability to study them. These advancements continue to push the boundaries of our understanding, providing scientists with the tools to probe the very fabric of the universe. Despite their elusiveness, neutrinos offer some of the most profound insights into fundamental physics. As researchers unravel their secrets, neutrinos offer a glimpse into the deeper mysteries of the cosmos. These particles remind us that even the most subtle clues, those that seem insignificant or nearly impossible to detect, can open doors to understanding some of the grandest phenomena in the universe. In the world of particle physics, accelerators stand as some of the most powerful tools for investigating the nature of matter. These machines accelerate particles, such as protons and electrons, close to the speed of light, enabling them to collide with enormous energy. These collisions recreate conditions similar to those just after the Big Bang, offering a window into the fundamental particles and forces that shape our universe. This type of research is critical in the search for answers to some of the most pressing mysteries of the cosmos, particularly when it comes to dark matter and antimatter. Dark matter is a truly enigmatic substance, making up roughly 25% of the universe's mass. Despite its prevalence, it does not emit, absorb, or reflect light, which makes it invisible to our current observational tools. Scientists have hypothesized that dark matter might consist of yet-to-be-discovered particles that differ entirely from the atoms we are familiar with. By recreating extreme conditions in particle accelerators, scientists hope to identify these hypothetical particles, such as weakly interacting massive particles or WIMPs. If such particles exist, these collisions could offer the first tangible evidence of dark matter, allowing researchers to better understand its properties. Antimatter, too, is a central subject of research in particle physics. It is the mirror image of normal matter, with every particle having an antimatter counterpart. When particles and antiparticles meet, they annihilate each other, releasing energy in the process. This symmetry between matter and antimatter raises a profound question. If equal amounts of both were created during the Big Bang, why does the universe seem to be dominated by matter? Particle accelerators allow scientists to produce controlled amounts of antimatter, enabling them to study its properties and interactions in a way that could potentially answer this question. Through this line of research, we are not just piecing together the nature of antimatter, but also examining the fundamental forces that dictate the very structure of the universe. Particle accelerators, through their high-energy experiments, provide a glimpse into realms of science that could completely reshape our understanding of the universe. Every new discovery, whether it confirms or challenges existing theories, ushers us closer to understanding the deeper workings of dark matter, antimatter, and the fundamental forces that govern everything. As each collision generates more data, it expands our horizon, forcing us to confront questions about the very composition of the universe, many of which remain unanswered. In a different, yet equally profound area of research, cosmic dust plays a crucial role in our understanding of the universe's evolution, particularly in relation to the life cycle of stars. These minuscule particles, floating between stars and galaxies, are composed of elements like carbon, silicon, and metals. Although seemingly insignificant, cosmic dust serves as the building block for the formation of stars and planets. In a way, it acts as both the raw material and the storyteller of the universe's ongoing process of creation. One of the key properties of cosmic dust is its ability to absorb and scatter light. Because of this, it can provide astronomers with a wealth of information about stellar nurseries, vast regions of space where new stars are born. Dust plays a particularly important role in cooling the surrounding gas through radiative processes. When dust and gas accumulate in certain regions of space, gravity takes over, pulling the material together and sparking the formation of new stars. As these particles interact with the radiation emitted by nearby stars, they offer a window into the temperatures and compositions of these environments, allowing scientists to uncover the conditions under which stars are born. Dust also plays a role in the death of stars, particularly in supernova explosions. When massive stars near the end of their life cycle, they may explode in a brilliant burst of energy and light. These explosions scatter dust and heavy elements into the surrounding space, enriching the interstellar medium and seeding the universe with the elements necessary for life. By studying the composition and distribution of this dust, scientists can piece together the history of specific star systems, offering insights into how elements like carbon and oxygen, vital for life, are formed and dispersed across galaxies. In the grand scheme of the universe, cosmic dust is much more than just space debris. It holds the story of star birth and death, of the processes that shape galaxies, and ultimately of the very elements that make up life as we know it. Through the study of cosmic dust, we gain a deeper understanding of how the universe evolves, how stars live and die, and how the building blocks of life are scattered across the cosmos. It is a reminder that even the smallest particles, seemingly insignificant on their own, can tell us the most profound stories of the universe's creation and ongoing transformation. Cosmic dust, often seen as mere specks drifting through the vast emptiness of space, holds much more than meets the eye. In fact, this tiny debris serves as a cosmic time capsule, preserving the chemical fingerprints of ancient stars and the environments in which they formed. By examining this dust, scientists can peer deep into the past, unraveling the history not just of our galaxy, but of the entire universe. In this way, cosmic dust acts as a key to understanding the origins and evolution of the very cosmos we inhabit. Through the study of cosmic dust, researchers gain invaluable insight into the process of stellar evolution, how stars are born, live, and eventually die. But its significance extends beyond just stars. Cosmic dust is essential for exploring the complex relationships between stars, planets, and the very building blocks of life. It bridges the gap between the stars themselves and the elements that form planets, atmospheres, and even life as we know it. This deep connection underscores the fundamental role cosmic dust plays in the story of the universe, tying together the origins of stars, the formation of planets, and the beginnings of life. A pivotal moment in our understanding of the universe came in 2012 with the discovery of the Higgs boson, a particle that has become almost legendary. This breakthrough was a monumental step forward in particle physics, directly linked to the Standard Model, a comprehensive framework that explains the fundamental particles and forces that govern the interactions of matter and energy. The Standard Model is a cornerstone of modern physics, unifying the 5 known forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces. The Higgs boson, often referred to as the God particle, is central to this framework, playing a crucial role in explaining why particles have mass. Before the Higgs boson was discovered, scientists had theorized that particles acquire mass through their interaction with an invisible field that permeates the entire universe, known as the Higgs field. As particles move through this field, they experience resistance, much like trying to swim through thick syrup, leading to the phenomenon we observe as mass. The Higgs boson itself is a manifestation or excitation of this field, much like ripples on the surface of water when a stone is thrown in. In the grander context of cosmology, the discovery of the Higgs boson holds even deeper implications, especially regarding the early universe. Immediately following the Big Bang, the universe was a seething mass of elementary particles existing in a hot, dense state. The Higgs field was undergoing significant changes as the universe expanded and cooled, and it was only through the interaction of particles with this field that they acquired the mass necessary to form the stars, galaxies, and planets that make up the universe today. The Higgs boson discovery not only confirmed a crucial component of the Standard Model, but it also opened new avenues for research into the very fabric of the universe. With the particle's discovery, scientists now turn their attention to questions that go beyond the Standard Model, seeking to understand the nature of dark matter and dark energy, 2 mysterious substances that constitute most of the universe, yet remain largely invisible to us. These unanswered questions represent the next frontier in physics, one that continues to inspire researchers and curiosity seekers alike. While the Higgs boson provides vital insight into the forces at play in our universe, there is yet another layer of mystery woven into the cosmic fabric: cosmic magnetic fields. These invisible forces permeate everything, from the tiny particles that make up interstellar dust to the enormous galaxies that stretch across the cosmos. While magnetism is a concept most of us are familiar with in simple forms, like the magnets on our refrigerators, the magnetic fields in space are far more complex and often exhibit strange anomalies that continue to baffle scientists. One such anomaly lies in the discrepancy between the observed magnetic field strengths in galaxies and the theoretical models that predict them. In some galaxies, magnetic fields are far stronger than expected, prompting researchers to reconsider how these fields are generated. Traditional theories suggest that magnetic fields arise from the movement of conducting fluids like plasma in stars and galaxies. Yet, in certain cases, the measured strengths of magnetic fields exceed what these models would predict. This suggests the involvement of other unknown processes or forces, such as turbulence in the intergalactic medium or interactions with cosmic rays. Another intriguing mystery concerns the spiral structures of magnetic fields within galaxies. While gravity is known to shape the overall structure of galaxies, the magnetic fields don't always follow these patterns. In some galaxies, the magnetic fields appear to be more chaotic and less orderly than the neat spiral arms of the galaxies themselves. This raises questions about the origins of magnetic fields and how they evolve. Some scientists speculate that these fields may have been influenced by past galactic events, such as galaxy mergers or supernova explosions that caused turbulence or disturbances in the magnetic structures. Perhaps the most enigmatic aspect of cosmic magnetic fields is their role in other cosmic phenomena. These fields are thought to play a crucial part in processes such as the acceleration of cosmic rays, the alignment of galaxies in clusters, and even the behavior of black holes. Despite their vast influence, the exact relationship between magnetic fields and observable cosmic structures is still not fully understood. As a result, scientists continue to probe deeper into the mysteries of the cosmos, hoping to unlock the secrets hidden within the complex web of magnetic fields that permeate the universe. This ongoing research not only challenges our understanding of cosmic magnetic fields, but also pushes us to confront deeper questions about the universe itself. It highlights the dynamic and sometimes unexpected nature of the cosmos, urging us to reconsider what we thought we knew and to remain open to the incredible complexity of the universe. Another captivating element of the universe is cosmic rays. high-energy particles that travel from deep space, carrying with them information about the distant reaches of the cosmos. These particles are messengers from the universe, offering clues about distant stars, galaxies, and even the most violent cosmic events. When cosmic rays collide with Earth's atmosphere, they create a cascade of secondary particles, which can be detected by specialized instruments. This process provides valuable data, allowing scientists to study these rays and learn more about their origins and the processes that occur in space. One of the most surprising findings from research on cosmic rays is the variability in their composition and energy levels. While many cosmic rays are thought to originate from supernova, the explosive deaths of stars, other potential sources remain elusive. Some scientists believe that these rays may come from active galactic nuclei, the supermassive black holes at the centers of galaxies, or even from gamma ray bursts, the most powerful explosions in the universe. As detectors capture these high-energy particles, researchers can analyze their composition and energy to detect patterns and anomalies that challenge current models of high-energy astrophysics. One particularly intriguing puzzle involves cosmic rays with energies so high that they seem to defy the limits of our current understanding. Some of these rays appear to have come from sources beyond our own Milky Way galaxy, sparking debates about the origins of these ultra-high-energy particles. What could be the engines behind such powerful particles? The mystery of these cosmic rays drives scientists to push the boundaries of what we know about the universe, inspiring new theories and research as we continue to explore the cosmic unknown. Interactions of cosmic rays with interstellar matter can trigger the production of various secondary particles, creating a web of intricate and often unexpected cosmic phenomena. These interactions not only lead to discoveries that stretch our understanding of the universe, but also sometimes reveal puzzling discrepancies, such as the underrepresentation of specific types of particles. This imbalance serves as a clue, hinting at possible gaps in our comprehension of fundamental physics, particularly the laws that govern particle dynamics and cosmic ray acceleration. The study of cosmic rays, therefore, does more than just deepen our understanding of high-energy astrophysics. It brings to light the complex, often elusive dynamics that govern the universe. Each new discovery, whether it's the unexpected behavior of a cosmic ray or the identification of a novel particle, pushes the boundaries of what we know and invites further questions. These breakthroughs allow researchers to revisit the foundational processes that shape the cosmos, helping us peel back the layers of mystery surrounding the very particles that travel through it. One of the most captivating phenomena in the cosmos involves astrophysical jets, often linked to the enigmatic black holes and neutron stars. These jets are colossal, powerful streams of particles and radiation, hurled out from the poles of these massive cosmic entities, creating some of the most striking and energetic events we can observe in the universe. Researchers closely monitor the structure, speed, and behavior of these jets because any anomaly can offer critical clues about the underlying forces and mechanisms at play in the extreme environments surrounding black holes and neutron stars. For example, when scientists detect unexpected variations in the shape or velocity of a jet, it may suggest that something unusual is taking place in the environment around the black hole. These anomalies could be the result of fluctuations in the accretion disk, the swirling mass of gas and dust surrounding the black hole, or alterations in the magnetic fields that govern the jet's structure. It could also point to previously unknown interactions with surrounding matter being pulled into the black hole's immense gravitational field. Such insights can refine our understanding of how black holes exert their influence on their surroundings and how these powerful jets are produced. Moreover, anomalies in the behavior of these jets often provide new clues about the black holes themselves. The characteristics of the jets, such as their speed, direction, and intensity, reveal much about the black hole's rotation, its mass, and the composition of the material that's spiraling toward it. When these observations don't align with existing models, they serve as a call to action for astrophysicists to reconsider established theories, potentially leading to new frameworks of understanding about the mechanics of black holes. In turn, these developments also shed light on their critical role in the evolution of galaxies, offering a more complete view of the forces that shape the universe. The search for anomalies within these cosmic jets isn't just about black holes. It's a quest to deepen our understanding of the universe as a whole. Each oddity observed is a vital piece of the puzzle, one that nudges us toward a more intricate and comprehensive view of the cosmos. Through these ongoing studies, scientists inch closer to unraveling the many mysteries of the universe, one anomaly at a time. In addition to these fascinating phenomena, one of the most thrilling endeavors for astronomers and scientists alike is the hunt for life beyond Earth, especially on exoplanets that orbit stars far outside our solar system. These distant worlds, with their unique environments, have become the focal point of intense study as we search for signs of life. Specifically, scientists are keen to detect biosignatures, which are indicators of past or present biological activity. These can take the form of certain gases or molecules that may only be produced by living organisms, providing critical evidence that life could exist or could have once existed on these distant planets. Among the most promising biosignatures are gases like carbon dioxide, oxygen, and methane. Their presence is particularly intriguing when two of them, oxygen and methane, are found together. On Earth, these gases coexist at significant concentrations, primarily due to biological processes. Oxygen is generated by plants and algae through photosynthesis, while methane is produced by microbes such as methanogens, which thrive in oxygen-free environments. Normally, these gases don't stay together for long because they react with each other and break down. Therefore, their simultaneous presence in a planet's atmosphere could be a sign of ongoing biological activity, making it an exciting marker for future exploration. Another crucial biosignature scientists look for is water vapor. Water is essential for life as we know it. It serves as the solvent for biochemical reactions and provides a stable environment for the complex processes that sustain life. Detecting water vapor in the atmospheres of exoplanets is an exciting step forward, as it suggests that a planet could host life, or at the very least, could provide a habitable environment. By observing seasonal fluctuations in water vapor, much like we do on Earth, scientists can also gain insights into the planet's geological and biological processes, offering further clues about the potential for life. Understanding biosignatures is vital not just for identifying potential habitats beyond Earth, but also for understanding the conditions that make life possible. A successful detection of biosignatures on exoplanets would be monumental. It could change our understanding of life in the universe, possibly confirming that we are not alone and radically shifting our perspective on Earth's own ecosystem. The search for biosignatures is thus much more than just a scientific pursuit. It's a profound journey into the unknown, one that challenges the very boundaries of human knowledge and our place in the cosmos. Moreover, the discovery of extremophiles on Earth has significantly expanded our understanding of the potential for life in extreme environments. Extremophiles are organisms that thrive in conditions once considered uninhabitable, such as deep-sea hydrothermal vents where temperatures exceed the boiling point of water, or highly acidic lakes, and even in the frozen tundras of the polar regions. These remarkable life forms have demonstrated that life is far more resilient than previously thought, able to endure environments that would be lethal to most other organisms. The study of extremophiles has provided invaluable insights into the types of environments that might harbor life on other planets. For example, if life can thrive in the acidic, superheated waters of a volcanic spring, similar organisms could potentially survive on planets or moons with comparable conditions. One prime candidate for this type of environment is Europa, one of Jupiter's moons. Beneath its icy surface, Europa is believed to harbor a subsurface ocean of liquid water, existing in a dark, high-pressure environment. If life can endure in such extreme conditions here on Earth, the same may be true for other celestial bodies with similar characteristics, making Europa and other moons an exciting focal point for the search for extraterrestrial life. These revelations are a game changer for astrobiology, reshaping our understanding of the limits of life and the conditions under which it can exist. As scientists continue to explore the far reaches of the universe, The possibility that life may thrive in places once thought inhospitable is becoming an increasingly tangible reality. Through these ongoing investigations, the boundaries of life's potential are expanding, allowing us to envision a broader and more diverse universe where life could exist in forms and places we once never imagined. The study of extremophiles has significantly broadened our understanding of life's potential to thrive in environments once thought to be inhospitable. These extraordinary organisms, which flourish in the most extreme conditions on Earth, such as boiling hot springs, deep-sea vents, or frozen deserts, have forced scientists to rethink the traditional criteria for habitability. In the past, researchers have focused primarily on planets that resembled Earth, particularly those with temperate conditions, moderate temperatures, and liquid water. However, as we continue to uncover the resilience of extremophiles, we are drawn to explore far more extreme environments in the cosmos. This new perspective has expanded our search for extraterrestrial life to include celestial bodies with harsh conditions such as high radiation, severe thermal fluctuations, and unique chemical compositions. These environments, once considered too extreme to support life, are now being seen as potential havens for life forms that are different from what we know on Earth. In fact, the study of extremophiles has revolutionized the way astrobiologists think about life beyond Earth, suggesting that life could exist in forms we have not yet imagined. As a result, scientists are now exploring places once considered uninhabitable, opening up the vast possibilities of life on other planets. The implications of this shift are profound. The existence of extremophiles has not only painted a more vivid picture of life's remarkable adaptability, but it has also sparked a sense of wonder and curiosity among researchers and the public alike. Their work has become a guiding force for missions aimed at exploring distant worlds. It pushes us to ask some of the most fundamental questions of our existence. How many forms of life are out there in the cosmos? Where might we find them? These questions continue to fuel the quest for knowledge as researchers seek answers in the vast expanse of space. Mars, often referred to as the Red Planet, has long been a focal point for humanity's fascination with the possibility of ancient life. Over the years, Mars has captured our imagination, especially with the tantalizing idea that it may have once hosted life. Recent explorations, particularly by NASA's rovers like Curiosity and Perseverance, have provided compelling evidence that suggests Mars was once home to a more hospitable environment. Among the most striking pieces of evidence is the discovery of ancient riverbeds and lake beds, geological features that point to the presence of liquid water on Mars billions of years ago. This was a time when the planet's surface conditions could have been conducive to life, offering a potentially welcoming habitat for microbial life to take root and thrive. In addition to the discovery of water, researchers have found organic molecules in Martian soil and rock samples. Organic molecules are the building blocks of life as we know it, composed of carbon, hydrogen, and other essential elements. Their detection in multiple locations across the Martian surface strengthens the case that Mars may have supported life at some point in its history. What makes this even more fascinating is that some of these organic molecules were found in formations that suggest they could have formed in the presence of water, further linking them to the ancient Martian environment that may have once supported life. One of the more intriguing findings from Mars missions is the detection of methane in its atmosphere. On Earth, methane is often produced by biological processes, particularly by microbes known as methanogens. The presence of methane on Mars raises intriguing possibilities. Could there be active biological processes occurring on Mars? Or could this methane be a sign of something else, like ongoing geological activity? The variations in methane levels detected by the rovers suggest that there may still be dynamic processes at work on Mars, hinting at the possibility of microbial life, or at least past life on the planet. Alongside these discoveries, the search for fossilized microbial life has guided some of the scientific missions to Mars. Scientists are currently investigating features that bear a striking resemblance to microbial mats, structures on Earth that were once the cradle of life in our planet's ancient oceans. If similar formations are found on Mars, they could provide the definitive evidence of past microbial life on the Red Planet. Ongoing missions, including those aimed at returning samples to Earth, hold the promise of uncovering more clues. These findings could one day lead to groundbreaking revelations, perhaps even proving the existence of ancient life on Mars and expanding our understanding of life beyond Earth. Beyond Mars, one of the most captivating bodies in our solar system is Titan, Saturn's largest moon. Titan presents an environment so radically different from Earth that it challenges our conventional thinking about where life might exist. This icy moon is enveloped by a thick atmosphere and features lakes and rivers filled not with water but with liquid methane and ethane. Titan's atmosphere and surface chemistry are unlike anything found on Earth, yet it has become one of the most intriguing environments for researchers who are interested in the possibility of life forms that do not require water in the way we understand it. The chemistry of Titan is particularly fascinating due to the presence of methane. On Earth, methane is largely produced by biological processes, specifically by microbes called methanogens. While Titan's methane is almost certainly not a product of life as we know it, its abundance suggests that the moon's environment may be suitable for radically different forms of life. The methane could interact with the complex chemistry in Titan's thick atmosphere, creating conditions where prebiotic molecules could form, perhaps even paving the way for life to emerge under entirely different biochemical principles than those on Earth. The possibility that Titan may harbor life, or at least provide the necessary conditions for lifelike chemistry to take place, makes it one of the most exciting targets for future space exploration. The ongoing study of Titan, particularly through missions like the Cassini spacecraft and the upcoming Dragonfly mission, promises to deepen our understanding of the moon's complex environment and the broader question of whether life can exist beyond the familiar conditions of Earth. In essence, the exploration of worlds like Mars and Titan, as well as the study of extremophiles on Earth, is reshaping our understanding of what life is and where it can exist. As we push the boundaries of what we thought was possible, we come closer to answering one of humanity's most profound questions. Are we truly alone in the universe? Scientists are increasingly intrigued by Titan, Saturn's largest moon, and its potential for harboring forms of life that defy conventional expectations. As researchers continue to probe Titan's extreme conditions, they are forced to rethink many long-held assumptions about the nature of life and the environments capable of supporting it. Titan's cold temperatures and lack of liquid water, fundamental to life as we know it, might not necessarily rule out the possibility of life. Instead, they could give rise to completely different biochemistries, where methane, rather than water, fuels the metabolic processes of hypothetical organisms. In this alien environment, life could potentially adapt to harness the energy from the abundant hydrocarbons that dominate the moon's atmosphere and surface. This prospect challenges our traditional understanding of what constitutes a habitable environment and urges us to expand our definitions of life. As we venture deeper into the exploration of Titan, researchers are not only studying its complex chemical composition, but also seeking out clues about the possibility of life that doesn't adhere to the water-based frameworks we rely on. Titan serves as a stark reminder that life may exist in forms we have yet to imagine, thriving in places and conditions we never considered viable. The search for life beyond Earth, spearheaded by astrobiologists, is propelled by the analysis of chemical signatures that may point to biological activity in distant worlds. These signatures come in the form of specific molecules that, in certain concentrations or combinations, suggest the presence of life, or at least the building blocks of life, on other planets or moons. Among the most tantalizing of these chemical signatures are those found in the atmospheres of exoplanets, which orbit stars far beyond our solar system. One of the most compelling gases for researchers is methane, which on Earth is often associated with biological processes. While methane can indeed be produced through geological means, its presence in combination with other gases, such as oxygen, hints at the possibility of biological origins. This combination of atmospheric elements creates a unique chemical fingerprint that could potentially indicate the existence of life. To search for such signatures, scientists employ cutting-edge telescopes and space missions equipped with sophisticated instruments capable of analyzing the composition of distant planets' atmospheres. The Kepler Space Telescope and the James Webb Space Telescope, launched with much anticipation, have provided invaluable insights into the conditions that could support life on exoplanets. Their observations are key to determining whether the atmospheres of distant planets are capable of sustaining life, thereby expanding the search for life far beyond our own solar system. Closer to home, missions to planets and moons within our own solar system, such as Mars, Europa, and Enceladus, provide direct access to samples of soil, water, and ice. These samples are analyzed for rare chemical signatures that could reveal the conditions in which life, if it ever existed, might have thrived. Each discovery, whether it is a new chemical trace or an anomalous reading, brings us one step closer to answering one of humanity's most profound questions. Are we alone in the universe? Yet it is not just the search for biological life that fascinates scientists. The cosmos itself is filled with celestial phenomena that challenge our understanding of the universe and spark wonder about the potential existence of intelligent life beyond Earth. Take, for example, the mysterious WOW signal detected in 1977. This unexplained burst of radio waves emanating from the direction of the constellation Sagittarius lasted just 72 seconds, and despite many efforts, it has never been repeated. The lack of a definitive source for this signal has fueled speculation that it could have originated from an intelligent extraterrestrial civilization. Another enigma that has puzzled astronomers is the behavior of Tabby's star, officially KIC 8462852, whose light curves show strange and irregular dimming patterns. While some scientists suggest that the dimming could be due to a cloud of comet debris, others entertain more exciting theories. One hypothesis posits that the dimming could be caused by enormous artificial structures, perhaps megastructures, constructed by an advanced civilization. Such structures, if they exist, could be harnessing the energy of the star itself, a concept that has captured the imagination of scientists and science fiction enthusiasts alike. In addition to these mysteries, another class of phenomena, fast radio bursts, FRBs, has taken center stage in recent years. These brief but intense bursts of radio waves originate from distant galaxies, and their origins remain largely unexplained. Some scientists propose that FRBs could be caused by extreme astrophysical events, while others wonder if these signals could be the product of advanced technologies from distant civilizations. Their enigmatic nature has led to numerous hypotheses, and each new discovery only deepens the mystery. Are these signals simply echoes from the violent universe, or could they be attempts at communication from intelligent beings? There are also peculiarities in the movements of celestial bodies in our own solar system that hint at the presence of unseen forces or masses. One such phenomenon is the potential existence of a ninth planet, often referred to as Planet 9. Many scientists believe that the gravitational anomalies observed in the orbits of distant objects in the Kuiper Belt could be explained by the presence of a yet unseen planet. However, some suggest that these anomalies might be caused by the influence of an advanced civilization, manipulating the orbits of objects for unknown reasons. While this remains a speculative theory, it highlights the fact that our exploration of the cosmos is still in its early stages, and the possibility of discovering new and unexpected phenomena is ever present. All of these mysteries, from the unexplained radio signals to the potential presence of advanced civilizations, serve to fuel our curiosity and drive our quest for knowledge. Every new discovery adds a new layer to our understanding of the universe and our place within it. The study of strange signals, anomalies, and unexplained cosmic events not only challenges our scientific models, but also invites us to think more broadly about the nature of life and intelligence in the universe. As we turn our gaze to the stars and the distant corners of the cosmos, we are reminded that the universe is full of surprises. One of the most intriguing areas of study is the detection of fast radio bursts, FRBs, which have become a major focus of astrophysical research since their first discovery in 2007. These bursts, which last only milliseconds but release an enormous amount of energy, have puzzled scientists ever since. Although some FRBs have been traced back to identifiable sources, Others remain completely unexplained, adding to the mystery and intrigue surrounding these cosmic phenomena. In addition to FRBs, pulsars, highly magnetized rotating neutron stars that emit beams of electromagnetic radiation, have also captured the interest of researchers. These beams sweep across space like a lighthouse beacon, and under certain conditions, the regularity of their pulses can be disrupted, creating a fascinating opportunity for study. Occasionally, pulsars exhibit irregularities in their rotation or unusual bursts of energy, leading scientists to question the environments around these dense, energetic objects. Perhaps most intriguing of all are the signals that suggest the possibility of extraterrestrial intelligence. Using powerful telescopes, scientists have detected periodic signals that exhibit specific patterns, leading some to speculate that they could be the result of advanced civilizations trying to communicate across vast distances. While most of these signals have been traced back to natural phenomena, the tantalizing possibility that some of them may represent genuine attempts at communication from intelligent life persists, keeping the dream of discovering extraterrestrial civilizations alive. The search for extraterrestrial intelligence, SETI, continues to be one of the most exciting and speculative areas of scientific research. The discovery of a single, repeatable signal from an intelligent source could radically alter our understanding of life in the universe and perhaps offer us our first evidence of extraterrestrial intelligence. Finally, interstellar dust, the tiny particles drifting between stars, offers an entirely different but equally fascinating avenue for exploration. These dust particles, remnants of ancient supernova explosions, provide valuable clues about the formation of elements that make up everything we know today. By studying these minute fragments of matter, scientists can trace the processes that led to the creation of the stars, planets, and life itself, offering a glimpse into the universe's earliest days. With each new discovery and every signal, we inch closer to understanding the vast and mysterious universe in which we live. Whether it's the detection of unusual signals, the study of interstellar dust, or the exploration of distant moons like Titan, each step we take brings us closer to answering one of humanity's most profound questions. Are we alone in the cosmos? The study of interstellar dust offers one of the most compelling glimpses into the very fabric of our universe. These tiny particles, scattered throughout the vast reaches of space, carry with them the chemical fingerprints of long-gone stars, revealing intricate details about the cosmos's past. The chemical makeup of this dust serves as a cosmic map, with its elemental ratios shedding light on the types of stars that gave birth to it. For example, the presence of certain heavy elements, often found in large amounts, points to cataclysmic events like supernovae, the violent explosions that occur when massive stars meet their fiery end. These stellar explosions disperse an extraordinary amount of material into the surrounding interstellar medium, enriching it with complex elements that would later come together to form new stars, planets, and even life itself. Through this process, scientists gain invaluable insights into the broader process of chemical evolution that shapes the universe, allowing them to understand how the basic building blocks of life and matter have evolved over billions of years. Moreover, interstellar dust functions as a type of time capsule, one that captures not just the elements that were present at its formation, but also the environments from which it originated. Each grain of dust can hold clues about its age, the conditions it was exposed to, and the stellar environments that created it. By studying these grains, researchers are able to piece together a cosmic timeline that traces the development of galaxies, stars, and planetary systems over billions of years. These dust particles are not just remnants of past events, but are also records of how the universe has evolved, revealing the complex interactions and forces that have shaped the galaxies we see today. Additionally, the study of interstellar dust helps expand our understanding of one of the universe's most elusive phenomena, the cosmic microwave background radiation. This faint, ancient glow is the remnant of the Big Bang itself, providing an essential clue to how the universe began and has evolved since. The way interstellar dust interacts with this radiation can offer valuable information about how energy and matter have moved and changed throughout space since the birth of the cosmos. By studying these interactions, scientists gain a deeper understanding of how the very fabric of the universe has been woven together over time, linking the birth of individual stars to the broader cosmic narrative. The relationship between interstellar matter, including gas and dust, and stellar winds also plays a crucial role in our understanding of the universe. Stellar winds, streams of charged particles ejected from stars, can significantly influence the interstellar medium, creating shock waves as they compress and heat the surrounding gas and dust. These interactions, observed across different wavelengths of light, from radio waves to X-rays, reveal key aspects of star formation, the remnants of supernovae, and the overall evolution of galaxies. By studying these processes, scientists can trace the movement and geometry of matter in space, shedding light on how stars and galaxies form and evolve. Yet, observation alone does not provide all the answers. To fully comprehend these cosmic interactions, researchers also rely heavily on computer simulations, which allow them to model and visualize the complex dynamics at play. These simulations simulate the behavior of gas, dust, and magnetic fields, as well as the radiation pressures exerted by stars. In this virtual environment, researchers can test hypotheses and refine their understanding of how stellar winds shape the interstellar medium, providing a clearer picture of cosmic dynamics. In addition to observations and simulations, laboratory experiments offer another crucial tool in studying these cosmic phenomena. By recreating conditions similar to those found in space, scientists can investigate how various elements and materials respond when subjected to forces similar to those generated by stellar winds. These experiments, though conducted on a smaller scale, provide valuable insights into the behavior of materials under extreme conditions, contributing to a more comprehensive understanding of the interaction between stellar winds and interstellar matter. All these efforts, the observations, simulations, and laboratory experiments, combine to offer a deeper understanding of the cosmic forces that shape our universe. By studying the complex interplay between stellar winds and interstellar matter, scientists can uncover the intricate, dynamic processes that govern the formation and evolution of galaxies, stars, and planetary systems. Moving beyond the interactions between stars and the interstellar medium, the Oort cloud represents an equally fascinating domain in our solar system, lying at the very outer reaches of our cosmic neighborhood. This vast spherical shell of icy objects, thought to extend from about 2,000 to 100,000 astronomical units AU from the Sun, remains largely theoretical, as it has yet to be directly observed. However, the existence of the Oort cloud is essential in explaining many phenomena within our solar system, especially the origins of long-period comets. These comets, which can take hundreds of years to complete their orbits, are thought to originate in the Oort cloud, where they are disturbed by the gravitational influence of nearby stars or molecular clouds, sending them on a path that brings them into the inner solar system. The Oort cloud is more than just a distant, mysterious region. It acts as a reservoir of ancient materials that hold clues about the early solar system. These icy bodies are effectively time capsules, preserving the primordial substances from over 4.5 billion years ago, offering scientists a direct window into the conditions that existed when the solar system was in its infancy. When these objects are disturbed and make their way into the inner solar system, they become visible as comets, their icy cores and tails serving as a reminder of the early days of planetary formation. The study of the Oort cloud also challenges our understanding of planetary formation and stability over vast timescales. The existence of such a distant cloud suggests that the solar system's history is far more complex than we once believed. It raises intriguing questions about the gravitational interactions that could have influenced the orbits and distribution of objects within the solar system, even those far from the sun's gravitational influence. These interactions invite researchers to rethink the dynamic forces that have shaped our solar system over billions of years, further complicating our understanding of planetary evolution. The Oort cloud is not just a theoretical curiosity. It is essential to our understanding of the solar system's composition and history. As a source of comets, it offers vital clues about the early solar system and the materials that ultimately formed the planets. In this way, it serves as a bridge between the ancient past and the present, helping us piece together the story of our solar system's formation, while continuing to influence the celestial environment we inhabit today. By studying the Oort cloud, scientists continue to unravel the mysteries of our cosmic origins and the dynamic forces that have shaped the solar system throughout its existence. In the vast and mysterious reaches of our universe, an ever-present sense of wonder fuels our scientific curiosity and exploration. This uncharted frontier continually inspires new research, urging us to understand the forces and phenomena that govern the cosmos. One such discovery in late 2017 provided a dramatic shift in our comprehension of space, as astronomers stumbled upon something truly extraordinary, a celestial object from beyond our solar system. This object, later named Oumuamua, meaning scout or messenger in Hawaiian, was the first confirmed interstellar traveler ever observed in our solar neighborhood. The elongated, cigar-shaped object was speeding through the vast emptiness of space at an astonishing velocity, sparking a frenzy of speculation and excitement within the scientific community and beyond. What made Oumuamua especially fascinating was its enigmatic origin. Unlike other asteroids or comets that are born from the same cosmic material within our solar system, Oumuamua hailed from a completely different star system. This meant that it was not merely a visitor to our solar system, but a celestial ambassador from the wider galaxy, carrying with it potential insights into the formation and dynamics of distant star systems. The very detection of Oumuamua opened up an entirely new field of study, the exploration of interstellar objects. Before this, the very notion of such objects had remained speculative at best. While scientists had theorized that objects like Oumuamua could be found outside the solar system, no concrete evidence had existed to support such claims. With its arrival, however, the concept of interstellar objects went from myth to reality. The unusual features of Oumuamua, including its rapid rotation and unexpected brightness, posed new questions that challenged established models of asteroid and comet behavior. Some scientists even wondered whether its characteristics could provide critical clues about the conditions necessary for life beyond Earth, prompting a fresh wave of questions about the nature of the universe and the potential for life elsewhere. This unprecedented discovery of an interstellar object like Oumuamua sparked an urgent interest in studying other interstellar visitors, with researchers turning their focus to comets and asteroids that could have originated from distant star systems. By analyzing these wandering objects, scientists gained valuable insights into the processes that shape not only our own solar system, but also the broader universe. In particular, the composition and trajectory of these objects reveal vital clues about the environments in which they formed, allowing astronomers to peer into the early stages of star and planet formation in far-off regions of space. One of the most intriguing aspects of these interstellar comets is their chemical makeup. Many of these objects contain organic compounds, water, and various ices, materials commonly associated with the building blocks of life. This has led to the tantalizing possibility that the fundamental ingredients for life may not be as rare as we once believed, and that the potential for life could exist on other worlds, even in systems far from our own. The presence of such life-sustaining materials on these interstellar bodies suggests that the elements necessary for life as we know it might be more widespread across the universe than previously thought. Even more intriguing is the possibility that these materials, carried on the winds of interstellar space, could be deposited onto distant planets or moons, seeding new worlds with the potential for life. But the mystery doesn't end there. The trajectory of these interstellar visitors can also reveal profound truths about the nature of our galaxy. Many of these objects have come from regions that are vastly different from our own solar system. Stellar nurseries, distant star clusters, or regions where stars are still being born. Tracking the paths of these interstellar wanderers allows astronomers to understand the gravitational forces at play in other parts of the galaxy, as well as the dynamics of the interstellar medium, the vast, often invisible substance that fills the space between stars. Through these studies, scientists are gaining new insights into the environment of distant star systems, offering a glimpse into how the broader universe operates. The study of interstellar comets is fast becoming a key to unlocking the mysteries of cosmic history. Each new discovery offers a fresh piece to the puzzle of how star systems evolve and how the fundamental components of planets and life come to be. The study of these far-flung objects enriches our understanding of the universe's origins and its ongoing evolution. As more interstellar objects are discovered, the opportunity to explore these questions expands, igniting the curiosity of scientists and space enthusiasts alike. In parallel, these interstellar discoveries are helping us to refine our understanding of the regions where new stars are born, the stellar nurseries. These vast, dense clouds of gas and dust, often found in the spiral arms of galaxies, are the birthplaces of stars. When we observe these cosmic nurseries, we can see the complex and delicate process by which new stars are formed. It all begins with the collapse of material under the force of gravity. As the gas clouds condense, they heat up, eventually reaching temperatures high enough to ignite nuclear fusion, the process that powers stars. The formation of stars in these regions is not an isolated event. Often, entire clusters of stars are born together, sharing the same primordial material. These star clusters, which can number in the hundreds or even thousands, provide invaluable insights into the life cycles of stars and their collective impact on the evolution of the universe. The chemical enrichment of the universe, for example, is deeply tied to the processes that occur in these stellar nurseries. As stars go through their life cycles, they create and release heavy elements that are critical to the formation of planets and life. Through the study of these star-forming regions, astronomers are gaining a deeper understanding of how stars evolve over time, from their early stages as massive gas clouds to their eventual death as supernovae or white dwarfs. Each stage in the life of a star contributes to the grand narrative of cosmic evolution. The study of stellar nurseries, combined with our growing knowledge of interstellar objects, is shaping our understanding of not just the birth of stars and planets, but the broader processes that govern the universe itself. In the end, each discovery about interstellar visitors or stellar nurseries serves to deepen our understanding of the vast, interconnected system of stars, planets, and cosmic phenomena. The more we learn, the more we are compelled to explore the many unanswered questions that continue to captivate our imagination. What is out there beyond our solar system? What mysteries lie hidden in the interstellar void? And perhaps most intriguing of all, are we truly alone in the universe? These are the questions that drive our exploration of the cosmos and keep our curiosity alive, fueling our relentless search for answers in the infinite expanse of space. Stellar nurseries, often referred to as the birthplaces of stars, offer an astonishing glimpse into the complexities of star formation. These vast, dense clouds of gas and dust are home to a diverse range of stellar creations, each shaped by a variety of environmental conditions. Some regions within these nurseries are responsible for the formation of massive stars, while others give birth to smaller ones. The differences between these areas are influenced by factors like temperature, density, and the overall composition of the surrounding matter. These variations dictate which types of stars will emerge from the gas and dust, painting a picture of the intricate, dynamic processes that unfold within these regions. By mapping out these stellar nurseries and observing stars at various stages of their development, scientists can gain a deeper understanding of the diverse environments that make up our galaxy. This process allows researchers to uncover the subtle differences that influence star formation, revealing how certain conditions favor the birth of specific star types. The more we observe these stellar nurseries, the more we realize how much they tell us about the intricate patterns that govern our universe. Moreover, studying stellar nurseries is essential for understanding the larger life cycle of matter in the cosmos. Stars are not static objects. They are part of an ongoing process of creation and destruction. Over the course of their lifetime, stars transform the material around them, synthesizing new elements within their cores. When they die, stars return this material back to space, enriching the interstellar medium with heavy elements such as carbon, oxygen, and iron. These elements, forged in the hearts of dying stars, are essential for the formation of new stars, planets, and even life itself. This cycle is not just fundamental to the birth of new celestial objects, but also to the ongoing evolution of galaxies. In this way, stellar nurseries are not simply fascinating points of interest. They are integral to the grand narrative of star formation and the continuous transformation of the universe. At the dawn of the universe, long before the first galaxies took shape, there were the first stars, known as population 3 stars. These early giants hold a special place in the story of our cosmic origins. They formed just 200 million years after the Big Bang, during a time when the universe was still in its infancy. Back then, the cosmos was a vastly different place, devoid of the complex elements that we now take for granted, such as carbon, oxygen, and iron. Instead, these first stars were made almost entirely of hydrogen and helium, the two simplest elements that emerged shortly after the Big Bang. Population 3 stars were extraordinary in size and mass, often many times more massive than the Sun. These stars could be tens or even hundreds of times more massive than our star. Their immense size and heat led to rapid fusion processes in their cores, causing them to burn hotter and faster than any stars we encounter today. Their short lifespans, lasting only a few million years, compared to the billions of years enjoyed by stars like our Sun, had a profound effect on the universe. These stars ended their lives in dramatic supernova explosions, scattering heavy elements like iron, nickel, and oxygen into the surrounding space. This contributed to the formation of later generations of stars known as population 2 and population 1 stars, which were composed of these newly created elements. The heat generated by population 3 stars also had a significant impact on the surrounding gas. Their radiation was so intense that it ionized the hydrogen gas in the early universe, helping to end the cosmic dark ages. During this period, the universe was mostly filled with neutral hydrogen gas, and light struggled to travel freely. The radiation from these first stars helped to ionize this gas, allowing light to travel more easily through space. This marked the beginning of a more illuminated universe, one that would eventually give rise to galaxies, stars, and planets. Even though we have yet to observe these population 3 stars directly, they remain a key area of research. Astronomers continue to study distant galaxies and employ advanced computational models to gain a better understanding of these enigmatic stars. Despite the challenges of observing objects that existed so long ago, the legacy of population 3 stars is crucial for understanding the evolution of our universe. Their formation, death, and contribution to the cosmic landscape provide us with valuable insights into the very beginnings of the universe and the subsequent formation of galaxies, stars, and other cosmic structures. In recent years, technological advancements have revolutionized our ability to explore the cosmos. In the early days of astronomy, our ancestors relied on the naked eye to observe the stars, tracking constellations, and documenting celestial events. With each leap in technology, from the invention of the telescope to the development of cutting-edge satellites, our view of the universe has expanded exponentially. These innovations have enabled us to peer deeper into space, uncovering details about distant galaxies and star systems that were once beyond our reach. Modern telescopes, equipped with state-of-the-art optics and digital sensors, have enhanced our ability to detect light from incredibly faint objects located millions, even billions, of light years away. Instruments like the Hubble Space Telescope have captured breathtaking images and gathered critical data, shedding light on the complex structures of galaxies, the birthplaces of stars, and the elusive nature of black holes. These breakthroughs allow us to study the very fabric of the universe, revealing its mysteries and helping us understand how galaxies evolve and interact over time. With each new observation, we are able to answer questions that were once unthinkable and uncover new layers of knowledge about the universe's vast, ever-changing landscape. The arrival of radio, infrared, and X-ray astronomy has fundamentally transformed our view of the universe. These different wavelengths have each unlocked a unique perspective on cosmic phenomena, shedding light on previously invisible aspects of the cosmos. Through radio waves, astronomers can detect the remnants of exploded stars or supernovae, whose visible light has long since faded. Infrared waves penetrate cosmic dust clouds, revealing hidden stars and planets that are otherwise obscured in optical wavelengths. X-rays, with their high energy, allow scientists to study the extreme conditions around supermassive black holes, where the gravitational forces are so intense they strip matter from surrounding stars and send it spiraling toward oblivion. The development of technology has not only made these observations possible, but also expanded the range of cosmic events that we can study. Instruments like gravitational wave detectors, a breakthrough that many see as a technological Easter egg, represent a major leap forward in our understanding of the universe. These detectors capture the ripples in space-time caused by massive events, such as the collision of two black holes, sending out waves of energy across the cosmos. This innovative method of listening to the universe provides an entirely new way to explore space, by detecting subtle vibrations in the fabric of space-time itself, rather than just observing light. These advancements do more than simply enhance our observational tools, they also deepen our comprehension of fundamental questions that have puzzled scientists for centuries. The more we observe, the closer we come to solving mysteries like the nature of dark matter and dark energy, the elusive substances that make up most of the universe's mass and energy. Each technological improvement builds upon the last, and with every new tool, we inch closer to understanding the origins of the cosmos and its future trajectory. As technology continues to evolve, so too will our ability to probe deeper into the universe's hidden corners, unveiling secrets that were once beyond our reach. Despite these advancements, astronomers face several challenges in their quest to understand distant galaxies. The most immediate obstacle is their vast distance from Earth. Light travels at a finite speed, meaning that when we observe distant galaxies, we are seeing them as they were billions of years ago, not as they are today. This time lag complicates efforts to form a complete and accurate picture of these far-off realms. What we see now is not necessarily a reflection of their current state, but a glimpse into their ancient past. Adding to this complexity is the faintness of the light emitted by these faraway galaxies. As light travels across the immense stretches of space, it loses intensity. This phenomenon makes it difficult for telescopes to gather enough light to resolve fine details. To overcome this, astronomers employ advanced techniques such as long exposure times, which allow instruments to collect light over extended periods. Yet even with this, the data remains challenging to interpret, as cosmic dust and gas between Earth and the galaxies can distort or obscure the light, altering the information we receive and complicating our understanding of their true nature. Moreover, most of our observations are limited to specific wavelengths of light, typically in the visible or optical spectrum, due to the constraints of current instruments. Many distant cosmic phenomena emit light outside of these wavelengths in areas such as the infrared or ultraviolet spectra. Without specialized telescopes capable of detecting these frequencies, astronomers are forced to overlook key aspects of galactic behavior, including details of their formation, evolution, and the interactions that shape them. Understanding galaxies, then, requires not just sensitivity to light, but versatility in detecting a broad range of electromagnetic radiation. The diversity of galaxies further complicates matters. Galaxies come in a wide range of shapes, sizes, and compositions. Some are spiral galaxies like our Milky Way, while others are elliptical or irregular in shape. Their interactions, such as collisions and mergers, can have unpredictable effects, sometimes triggering the formation of new stars, and other times leading to the destruction of existing ones. Studying nearby galaxies can offer some context, but applying those findings to distant galaxies is a complex challenge. The farther a galaxy is, the less certain we become about its structure, behavior, and history. Despite these hurdles, technology continues to advance, and as new instruments are developed, astronomers are uncovering more about the cosmos. Every new discovery provides deeper insights, not just about distant galaxies, but about the universe as a whole. We are learning more about our place in this vast, mysterious expanse with each breakthrough. In this ever-evolving landscape, citizen science is proving to be an invaluable asset. Ordinary people, often without formal scientific training, are contributing to significant astronomical discoveries. Thanks to the internet and advances in technology, anyone with a passion for space can engage in real scientific research. One of the most striking examples of this is the discovery of new celestial bodies through collaborative citizen science projects like Galaxy Zoo. Here, volunteers are invited to classify images of galaxies, sorting them by their distinct features, such as spiral arms or central bars. This simple act of categorization, done at scale, enables scientists to process vast amounts of data much faster than they could on their own. These classifications provide crucial insights into the formation and evolution of galaxies, offering a level of detail that would be impossible to achieve through traditional research methods alone. Citizen scientists bring a fresh perspective and enthusiasm that invigorates the process, underscoring the power of collaboration between professionals and amateurs. Through these efforts, more is being revealed about the universe's past and present, opening up exciting new possibilities for discovery and understanding. Citizen scientists play an essential role in the ever-expanding exploration of our universe, often standing at the forefront of astronomical research and discovery. These everyday observers, driven by passion and curiosity, are dedicated to monitoring and documenting astronomical events, tracking transient objects like supernovae, novae, and asteroids. By reporting their findings through specialized platforms designed for collaborative research, they contribute valuable data that enhances our understanding of these fleeting phenomena. Without the keen eyes of these volunteers, many significant discoveries, such as previously unnoticed supernovae, may remain hidden from the scientific community. Citizen science is more than just data collection. It fosters a powerful sense of community engagement and scientific inquiry. It invites a broad and diverse group of people, regardless of their professional background or formal training, to contribute their time and effort to the pursuit of knowledge. By doing so, these individuals deepen their personal connection to the cosmos, becoming active participants in a much larger endeavor. Through these collective efforts, not only is our understanding of the universe advanced, but a profound sense of wonder is sparked in the hearts of all involved. In many ways, citizen scientists help remind us that the universe, vast and mysterious, is waiting to be explored. One particularly fascinating phenomenon that captivates both professional astronomers and amateur stargazers alike is gravitational lensing. This occurs when a massive object, such as a galaxy or a galaxy cluster, bends the light from a distant object behind it. It's a process similar to how a glass lens can distort and magnify an image. Because light travels at a constant speed through space, when it encounters a massive object, the gravitational field of that object can warp the light's path. This bending of light not only magnifies the distant object, but also allows astronomers to observe galaxies that would otherwise be too faint or distant to see. This optical phenomenon can produce multiple images of the same object, depending on the positioning of the massive object relative to the distant galaxy. In some cases, these images appear as arcs, or in more spectacular cases, as complete rings, famously known as Einstein rings. These visual marvels provide astronomers with invaluable insights into the universe's history, offering views of galaxies from when the universe was much younger. Studying these distant galaxies helps trace their evolution over billions of years. But gravitational lensing doesn't only expand our view of the universe, it also provides critical information about dark matter. Dark matter, which does not emit light and remains invisible, can only be detected through its gravitational effects on visible matter. By studying the way light bends as it passes through a gravitational lens, scientists can map the distribution and concentration of dark matter within galaxies and clusters. This phenomenon plays a crucial role in revealing the universe's hidden structure and the gravitational forces that shape it. Gravitational lensing, then, is not merely an optical illusion. It's an essential tool for astronomers, allowing them to look deeper into the fabric of the cosmos and understand the unseen forces at work. Collaborations between observatories across the globe have revolutionized our understanding of the universe. Imagine countless pairs of eyes, each directed at the heavens, equipped with unique instruments and perspectives, working together to piece together the vast celestial puzzle. By sharing data, resources, and expertise, these observatories create a much clearer picture of the universe than any single institution could ever hope to achieve. One of the most significant advantages of global cooperation is the ability to observe astronomical events from different locations and at different times. The Earth's rotation and its orbit around the Sun mean that the view of the night sky constantly shifts. By coordinating efforts, astronomers can track transient phenomena, such as the dramatic explosion of a supernova or the sudden appearance of a comet, more accurately. This global collaboration ensures that these rare and fleeting events can be observed more comprehensively, enhancing both the duration and the quality of observations. Additionally, different observatories specialize in observing various wavelengths of light, such as radio, infrared, and ultraviolet, each revealing distinct information about the celestial objects they study. The rise of big data and cutting-edge technologies has further propelled these collaborations. With the help of sophisticated algorithms and powerful computational resources, astronomers can now analyze vast amounts of data with unparalleled efficiency. One notable example is the Event Horizon Telescope, which famously captured the first ever image of a black hole. Such breakthroughs would be impossible without the global network of observatories working together toward a shared goal. Collaborations like these not only push the boundaries of scientific discovery, but also inspire future generations of scientists. As new cosmic maps are created and updated, we gain an increasingly detailed understanding of the universe, and from the stars and galaxies to the mysterious dark matter that constitutes much of the cosmos. Technology and innovation have empowered us to chart the universe in ways that were once unimaginable, unveiling new insights into the structure and composition of the universe. However, updating these maps is no small task. The universe is vast, and distances between celestial objects are staggering, often measured in light years. Observing these objects and tracking their movements over time can be an incredibly complex challenge. On top of that, many astronomical phenomena are transient. Supernovae and meteors, for example, are fleeting, changing quickly in ways that can be difficult to capture. To accurately update our cosmic maps, astronomers must employ sophisticated telescopes and techniques to observe these brief but crucial events. The sheer volume of data generated by each new observation is another hurdle. Whether it's the intricate details of a distant galaxy or an expansive catalog of stars, sorting through this data requires advanced computational techniques. Ensuring the accuracy and consistency of measurements, especially when combining data from various telescopes and missions, adds further complexity to the task. Scientists must continually refine their methods to improve the precision of their cosmic maps, ensuring that each update is as accurate as possible. Yet perhaps the most profound challenge lies in the philosophical implications of mapping the cosmos. With every update and new discovery, we come closer to answering fundamental questions about the nature of the universe, questions about time, space, and gravity. Each new breakthrough shifts our understanding of these core concepts, challenging and expanding our perception of reality itself. The act of creating and updating these maps, then, is not simply a matter of recording positions and movements. It's a journey that deepens our connection to the universe and reminds us of the vastness and complexity of the cosmos. In the end, these efforts remind us of how much we still have to learn. Despite the tremendous progress we've made in mapping the universe and understanding its workings, the more we discover, the more questions arise. The universe is an endless frontier, one that will continue to inspire awe and wonder as we continue to chart its mysteries and unlock its secrets. Each update to our cosmic maps is a step forward, not just in science, but in humanity's eternal quest to understand its place in the vast expanse of the cosmos.